Hello, dear viewer. You're on the Sleepy Encyclopedia channel. Today you will plunge into the full story of dinosaurs, the ancient rulers of Earth whose history began more than 230 million years ago. You will learn how the first small dinosaurs appeared, how they rose to dominate the land, how giants, predators, feathered creatures, and early birds shaped the Mesozoic world, and how their age came to an end. Lie back and enjoy watching. Chapter 1. Before the Dinosaurs, a World Without Giants. Long before the first dinosaur walked across the Earth, the planet was already ancient, restless, and full of life. The story of dinosaurs does not begin with towering giants, roaring predators, or peaceful herds moving through fern-covered valleys. It begins in a wounded world, a world that had survived the greatest disaster in the history of life. About 252 million years ago, at the boundary between the Permian and Triassic periods, Earth passed through a catastrophe so severe that it nearly emptied the planet. This event, known as the Permian-Triassic Extinction, destroyed most marine species and a very large share of life on land. Forests collapsed, reefs vanished, food chains broke apart, and entire groups of animals disappeared forever. The causes were complex, but enormous volcanic eruptions in what is now Siberia released vast amounts of gases into the atmosphere, changing the climate, warming the planet, acidifying the oceans, and disturbing the delicate balance of life. In this devastated world, there were no dinosaurs yet. There were no familiar mammals, no flowering plants, no birds, no grass, and no modern forests. Instead, the Earth was dominated by strange survivors, animals that seem almost alien when compared with the life we know today. The continents were joined together into one immense supercontinent called Pangaea, a gigantic landmass surrounded by a vast global ocean. Because so much land was far from the sea, many regions were dry, hot, and seasonal. Deserts stretched across the interior, rivers cut through dusty plains. The climate could be harsh and unstable, especially for animals trying to recover after extinction. Yet life did not vanish. It adapted. It returned, slowly, unevenly, and with remarkable creativity. In the early Triassic world, many of the most important land animals were not dinosaurs, but other reptiles and distant relatives of mammals. Among them were the synapsids, a broad group that included the ancestors of mammals. Some of these creatures, such as Lystrosaurus, were squat, beaked herbivores that became extremely common after the extinction, almost as if they had inherited an empty world. There were also early archosaurs, a group of reptiles whose descendants would eventually include crocodiles, pterosaurs, dinosaurs, and birds. At first, dinosaurs were only a possibility hidden inside this larger evolutionary family. The land was not waiting for them. They had no guaranteed throne. Other creatures were already experimenting with different ways of living, moving, eating, and surviving. Some animals walked on sprawling limbs, with their legs extending out to the sides like modern lizards. Others began to hold their limbs more directly beneath the body, a change that allowed more efficient movement across land. This shift in posture may seem like a small anatomical detail, but it was one of the great innovations of the Triassic world. Animals with upright limbs could walk and run more effectively, carry their bodies with less wasted energy, and perhaps travel farther in search of food and water. The ancestors of dinosaurs belonged to this changing world of upright, agile archosaurs. They were not yet gigantic. They were not yet dominant. They were small, lightly built animals living among larger and more powerful competitors. To imagine the world before dinosaurs, it is important to remove the image of endless green jungles filled with monsters. The earliest stage of their story was more austere. The plants were mostly conifers, seed ferns, cycads, ginkgos, horsetails, and other ancient lineages. There were no flowers brightening the landscape and no fruits in the modern sense. Forests existed, but they were not like today's forests. In many places, vegetation had been badly reduced by extinction and climate stress, leaving open landscapes where survival depended on endurance. Insects, amphibians, reptiles, and early mammal relatives occupied the recovering ecosystems. Rivers and lakes were important refuges. Coasts and floodplains could support richer life than the dry interiors of Pangaea. The oceans were also rebuilding after devastation, slowly filling again with fish, marine reptiles, ammonoids, and other organisms that would later form the backdrop of the Mesozoic seas. The absence of dinosaurs in this early chapter is exactly what makes it important. It reminds us that dinosaurs were not the beginning of life's story, but a later development in a much older drama. Before them came billions of years of evolution, countless experiments in anatomy and behavior, and several mass extinctions that repeatedly reshaped the planet. The world that produced dinosaurs was a world of recovery. Empty ecological spaces had opened. Old rulers had fallen. New groups had room to expand. Evolution does not plan ahead, but it responds to opportunity. And after the Permian extinction, opportunity existed everywhere. Still, opportunity alone was not enough. Animals had to survive drought, heat, competition, disease, predators, and sudden environmental changes. The line that would eventually lead to dinosaurs passed through this difficult filter. Their ancestors were small enough to be flexible, active enough to exploit new niches, and anatomically suited for efficient movement. Over time, these features would matter enormously. The supercontinent Pangaea also played a crucial role. Because the land masses were connected, animals could spread widely without crossing oceans. At the same time, the interior of Pangaea created extreme climates that tested life in powerful ways. Seasonal rains, long dry periods, and broad open regions may have favored animals that could move efficiently and adapt to changing resources. Early dinosaur relatives lived in this world alongside crocodile-line archosaurs, large amphibians, mammal-like reptiles, and many other creatures now known mostly from fossils. Some of these animals were more impressive than the earliest dinosaurs. Some were larger, more abundant, or more ecologically important. If someone could have stood in the middle Triassic and tried to predict the future, they might not have chosen dinosaurs as the coming rulers of Earth. They were still modest players in a crowded evolutionary theater. This is one of the most fascinating ideas in paleontology. Dominance often begins quietly. The animals that later became symbols of prehistoric power began as small survivors on a damaged planet. The first dinosaurs did not appear with thunder. They emerged gradually from a world still healing from catastrophe. Their rise was connected to climate, geography, extinction, anatomy, and chance. Before the Age of Giants, there was an age of recovery. Before Tyrannosaurus, Triceratops, Stegosaurus, and Brachiosaurus, there were dry plains, ancient reptiles, struggling forests, and small, agile archosaurs moving through the shadows of a world that had almost ended. The full story of dinosaurs begins here, not with their triumph, but with the fragile conditions that made their existence possible. In the silence after the greatest extinction Earth had ever known, life began again, and among the many creatures searching for a future, one lineage slowly took its first steps toward becoming the most famous animals in the history of the planet. Chapter 2. The First Dinosaurs. The first dinosaurs did not resemble the gigantic creatures that most people imagine when they hear the word dinosaur. They were not towering predators, enormous, long-necked herbivores, or heavily armored giants. Instead, they were relatively small, lightly built animals that lived in a world crowded with competitors. Their story began during the late Triassic Period, roughly 230 million years ago, when Earth looked very different from today. All major continents were still joined together as part of the immense supercontinent Pangaea. Vast deserts stretched across its interior, seasonal rains shaped river valleys and floodplains, and life was still recovering from the catastrophic extinction that had nearly destroyed the biosphere millions of years earlier. In this challenging environment, the ancestors of dinosaurs were just one branch among many members of the Archosaur family, the great reptilian group that also gave rise to crocodilians and pterosaurs. For much of the Triassic, dinosaurs were not dominant. They lived alongside a remarkable variety of reptiles, many of which seemed better adapted to the world around them. Some crocodile-line archosaurs grew much larger than the earliest dinosaurs. Others occupied ecological roles that dinosaurs would later claim for themselves. Yet hidden within these early populations were anatomical features that would eventually help dinosaurs become one of the most successful groups of land animals in Earth's history. One of the most important differences involved posture. Many earlier reptiles carried their limbs out to the sides of their bodies. Dinosaurs, however, evolved a more upright stance, with their legs positioned directly beneath them. This arrangement allowed for more efficient movement, greater endurance, and improved speed. Rather than waddling or sprawling, dinosaurs could walk and run with remarkable effectiveness. Although this may seem like a minor anatomical change, it provided advantages that became increasingly important as environments shifted and competition intensified. The earliest known dinosaurs appeared in regions that today are part of South America, particularly areas of modern Argentina and Brazil. At the time, however, these regions were not separate continents but connected portions of southern Pangaea. Fossils discovered there have provided some of the most valuable clues about the origins of dinosaurs. Among the most famous early dinosaurs is Eoraptor, whose name means dawn thief. Living around 231 million years ago, Eoraptor was a small, agile animal about the size of a medium dog. It possessed a slender body, long tail, sharp claws, and a lightweight skull equipped with teeth suited for a flexible diet. Scientists continue to debate exactly where Eoraptor belongs on the dinosaur family tree, but its primitive features make it one of the most important fossils for understanding dinosaur origins. Another significant early dinosaur was Herrerasaurus, a larger predator that could reach several meters in length. With powerful hind legs and sharp teeth, it was among the top hunters of its environment. Herrerasaurus demonstrates that even very early in their history, some dinosaurs had already evolved into effective carnivores. Yet, despite their hunting abilities, these animals did not dominate their ecosystems. They shared the landscape with many other predators and prey species, all competing for survival. One fascinating aspect of early dinosaur evolution is how quickly diversity emerged. Within a relatively short geological period, dinosaurs began branching into different forms adapted to different lifestyles. Some became carnivores, pursuing insects, small reptiles, and other animals. Others evolved toward herbivory, feeding on vegetation that covered the Triassic landscape. This divergence eventually produced the two great branches of dinosaur evolution: the Saurischians and the Ornithischians. The Saurischians included theropods, which later gave rise to famous predators such as Tyrannosaurus rex and ultimately to birds, as well as sauropodomorphs, the ancestors of giant, long-necked dinosaurs. The Ornithischians included future groups such as stegosaurs, ankylosaurs, and ceratopsians. At the time, however, these future dynasties were still in their infancy. The first dinosaurs were relatively modest creatures, whose descendants would eventually transform the world. The Triassic ecosystems they inhabited were dynamic and often unstable. Climate fluctuations could drastically alter habitats. Droughts, floods, volcanic activity, and changing vegetation created constant challenges. Such instability may actually have benefited dinosaurs. Their upright posture, active lifestyles, and efficient movement allowed them to exploit opportunities that appeared when environmental conditions changed. While some competing groups remained highly specialized, early dinosaurs often displayed a degree of flexibility that may have helped them survive difficult periods. Fossil evidence suggests that many early dinosaurs grew quickly compared with other reptiles. Studies of fossilized bones reveal growth patterns indicating relatively rapid development. Faster growth can provide numerous advantages. Young animals become less vulnerable to predators, reach reproductive maturity sooner, and respond more effectively to environmental pressures. Although scientists continue to study dinosaur physiology, evidence increasingly suggests that even the earliest dinosaurs may have possessed higher activity levels than many traditional reptiles. This does not necessarily mean they were fully warm-blooded in the modern sense, but they likely occupied a metabolic middle ground that gave them advantages in movement and endurance. Another important feature of early dinosaurs was their hands. Many possessed grasping forelimbs with flexible fingers capable of manipulating food or capturing prey. Combined with forward-facing eyes and agile bodies, these adaptations helped some species become effective hunters. Others developed longer necks that allowed them to reach vegetation more efficiently. Small evolutionary changes accumulated over millions of years, gradually producing the extraordinary variety that would characterize later dinosaur ages. The spread of dinosaurs across Pangaea was facilitated by the geography of the supercontinent itself. Because continents remained connected, animal populations could expand across enormous distances without crossing major oceans. Over time, dinosaur fossils begin appearing in regions that today belong to North America, Europe, Africa, and Asia. This distribution demonstrates how rapidly the group expanded from its probable southern origins. However, expansion did not immediately equal dominance. For millions of years, dinosaurs remained only one component of complex ecosystems. Their eventual rise required another major event. Near the end of the Triassic Period, approximately 201 million years ago, Earth experienced another mass extinction. Although not as devastating as the Permian catastrophe, this event eliminated many groups of reptiles that had competed directly with dinosaurs. Massive volcanic eruptions associated with the breakup of Pangaea released enormous quantities of gases into the atmosphere, triggering climate disruption on a global scale. Many species disappeared. Entire ecological niches suddenly became vacant. When the extinction ended, dinosaurs were among the survivors. This moment proved crucial for their future success. With many competitors gone, dinosaurs rapidly expanded into newly available roles. They diversified into larger forms, occupied a greater variety of habitats, and became increasingly dominant across terrestrial ecosystems. Yet all of this lay in the future. The true story of the first dinosaurs is not one of immediate conquest, but of gradual adaptation. They began as small animals living among larger and often more impressive neighbors. Their success was not guaranteed. Had environmental conditions changed differently, had certain extinctions not occurred, or had competing groups survived in greater numbers, dinosaurs might never have become the rulers of the Mesozoic world. Instead, they may have remained a minor branch of reptilian evolution known only to paleontologists. What makes the first dinosaurs so fascinating is precisely their modest beginning. The ancestors of Tyrannosaurus, Triceratops, Brachiosaurus, and every other famous dinosaur started as small, adaptable creatures navigating a difficult and uncertain world. They inherited a planet shaped by extinction, climate change, and fierce competition. Through a combination of anatomical advantages, ecological flexibility, and fortunate timing, they survived where others vanished. Their rise was not sudden, but gradual, unfolding over millions of years as evolution slowly transformed a handful of unremarkable reptiles into the ancestors of some of the most extraordinary animals ever to walk the earth. The age of dinosaurs had not fully arrived yet, but its foundations were being laid by these early pioneers, whose small footsteps would eventually echo across an entire era of planetary history. Chapter 3. Pangaea, the supercontinent of dinosaurs. To understand the early story of dinosaurs, it is impossible to ignore the world they were born into, because dinosaurs did not first appear on a planet divided into the familiar continents of today. They emerged on Pangaea, the great supercontinent, a single, immense landmass that gathered together nearly all of Earth's major continental crust. North America, South America, Africa, Europe, Asia, Antarctica, Australia, and India were not yet separated by wide oceans. They were joined into one colossal geological stage, surrounded by the vast global ocean Pangaea and bordered in some regions by the Tethys Sea. This arrangement shaped climate, migration, evolution, and survival in ways that deeply influenced the rise of dinosaurs. Pangaea was not just a map detail, it was one of the main characters in the story. When the first dinosaurs appeared during the late Triassic Period, around 230 million years ago, this supercontinent created a world of extremes. Because so much land was concentrated in one continuous mass, many interior regions lay far from the cooling and moistening influence of the sea. The result was a planet with enormous dry zones, broad deserts, seasonal climates, and sharp contrasts between wet coastal regions and harsh inland basins. In some places, rivers carved through red floodplains. In others, dunes, dry valleys, and open scrublands stretched for great distances. The world was warm, and there were no polar ice caps like those of the modern age. Even high-latitude regions could support forests, though the distribution of plants and animals depended heavily on rainfall, altitude, and local geography. For early dinosaurs, this meant that survival was tied to movement, endurance, and adaptability. Pangaea allowed animals to spread across huge areas without crossing oceans, but it also forced them to endure climates that could be difficult and unpredictable. The earliest dinosaurs probably originated in the southern part of Pangaea, in a region known as Gondwana, especially in what is now South America. Fossils from Argentina and Brazil show that small, agile dinosaurs were already living there in the late Triassic. But because the continents were connected, their descendants and relatives could gradually expand into other parts of the supercontinent. This is one reason dinosaur fossils eventually appear across many modern continents. They did not need ships, land bridges, or rare accidents to cross from one continent to another. The land itself was connected. A dinosaur population could spread generation by generation, following river systems, forest margins, open plains, and shifting habitats. Over long spans of time, this connected world helped early dinosaurs become a widespread group. Yet Pangaea did not make life simple. A connected continent does not mean a uniform continent. Mountains, deserts, climate belts, volcanic regions, and seasonal barriers could still separate populations. Some groups became isolated in particular basins or regions, while others expanded widely. This combination of connection and separation is important in evolution. When populations spread, they encounter new environments. When they become isolated, they can change in different directions. Over millions of years, this process helped create diversity. Early dinosaurs were not all the same. Some were small carnivores, some were omnivores, and some began moving toward plant-eating lifestyles. Their world gave them space to experiment, and Pangaea provided that space on a magnificent scale. The plants of Pangaea also shaped dinosaur life. This was not a world of grasses, flowers, apples, or broad modern meadows. Flowering plants had not yet become dominant. Instead, the landscapes of the Triassic and early Jurassic were filled with conifers, cycads, ginkgos, seed ferns, horsetails, and other ancient plant groups. In wetter regions, forests could grow along rivers and lakes. In drier places, vegetation may have been more scattered, forcing herbivores to travel in search of food. For the earliest plant-eating dinosaurs and their relatives, feeding on these tough plants required anatomical changes. Teeth, jaws, necks, digestive systems, and body size all mattered. Over time, some dinosaur lineages evolved longer necks and larger bodies, allowing them to reach more vegetation and process more food. The later rise of giant sauropods can be partly understood against this background. On a huge continent full of ancient vegetation, animals that could efficiently gather and digest large amounts of plant material had enormous evolutionary potential. Pangaea also influenced predators. Open habitats and seasonal landscapes favored animals that could move well and cover distance. The upright posture of dinosaurs, with legs held beneath the body, may have been especially useful in such environments. A small predatory dinosaur moving through a dry basin could travel more efficiently than a sprawling reptile of similar size. This did not make dinosaurs instant rulers, but it gave them useful advantages. During much of the Triassic, many top predators were not dinosaurs at all. Crocodile-line archosaurs and other reptiles occupied powerful positions in the food web. Some were heavily armored, some were large hunters, and some resembled strange experiments in reptilian design. Dinosaurs lived among them, sometimes as predators, sometimes as prey, and sometimes as quiet survivors. Their future greatness was still hidden. The supercontinent also played a role in extinction and renewal. Pangaea did not remain stable forever. Deep beneath the crust, Earth's internal heat continued to move plates, stretch continents, and open cracks in the land. Toward the end of the Triassic period, the supercontinent began to break apart. This breakup was not gentle. It was associated with enormous volcanic activity, especially in what would become the Central Atlantic region. Vast eruptions released gases into the atmosphere, contributing to climate disruption and helping trigger the Triassic-Jurassic mass extinction around 201 million years ago. Many competing reptile groups declined or vanished. Dinosaurs, however, survived and expanded. The breakup of Pangaea, therefore, became one of the turning points in their history. The same supercontinent that had allowed their early spread also helped create the environmental crisis that cleared the way for their later dominance. After this extinction, dinosaurs entered the Jurassic Period, with far fewer rivals in many land ecosystems. As Pangaea continued to split, the world changed again. New coastlines appeared, rift valleys opened, seas advanced into lowlands. Continents slowly drifted apart, and dinosaur populations that had once lived on connected lands became separated by widening oceans. This isolation encouraged new evolutionary paths. Dinosaurs in one region could begin to differ from dinosaurs elsewhere. Over time, the breakup of Pangaea helped produce the rich regional diversity of the Jurassic and Cretaceous worlds. The dinosaur age, then, was shaped by both unity and division. First, the unity of one great landmass, then the division of that landmass into continents with their own climates, plants, and animal communities. Pangaea reminds us that dinosaurs were never separate from the planet beneath their feet. Their evolution was tied to moving plates, changing climates, volcanic eruptions, ancient seas, and the geography of continents. They were biological creatures, but their story was also geological. The bones found today in Argentina, Brazil, the United States, Morocco, Germany, China, and many other places are scattered across modern nations, yet they belong to a much older world, in which those lands were arranged differently. Every fossil is not only the remains of an animal, but also a clue to a vanished map. When we imagine the first dinosaurs, we should not picture them walking across isolated continents like those of the modern globe. We should imagine them moving through Pangaea, a massive, warm, often dry world where deserts and river valleys stretched across connected lands, where ancient plants grew beneath unfamiliar skies, where competitors were many, and where the future was still uncertain. The supercontinent gave dinosaurs room to spread, challenges to overcome, and opportunities to evolve. It created the stage on which their earliest history unfolded and set in motion the changes that would eventually lead to their rise. Before dinosaurs became the rulers of the Jurassic and Cretaceous worlds, they were children of Pangaea, shaped by its vastness, tested by its climates, and carried by its connected lands into the beginning of one of the greatest chapters in the history of life. Chapter 4. The Triassic World. The Triassic World was one of the strangest and most important stages in the history of life, because it was both an aftermath and a beginning. It began after the greatest mass extinction Earth had ever experienced, and it ended with another extinction that would open the way for dinosaurs to become dominant. Between those two disasters stretched a period of recovery, experimentation, and transformation. The Triassic period lasted from about 252 million to 201 million years ago, and during this time, the planet was still marked by the wounds of the Permian extinction. Life had survived, but it had not simply returned to its old form. Many ancient groups were gone forever, and the ecosystems that rebuilt themselves were new, unstable, and filled with opportunity. The world was united into the supercontinent Pangaea, surrounded by the global ocean Panthalassa, with the Tethys Sea cutting into its eastern side. This geography created a planet of extremes. The interior of Pangaea was often hot, dry, and far from the moisture of the sea. Vast deserts and seasonally dry plains stretched across enormous regions. In other places, especially near coasts, rivers, lakes, and monsoon-influenced zones, life could be richer and more varied. There were no flowering plants, no grasslands, no familiar modern forests, and no birds singing in the trees. The vegetation was ancient and unfamiliar. Conifers, cycads, ginkgos, seed ferns, horsetails, mosses, and ferns formed the green framework of the landscape. In wetter areas, forests and dense riverbank vegetation provided food and shelter. In drier areas, plants grew more sparsely, forcing herbivores to travel and adapt to seasonal shortages. The atmosphere, climate, and landforms of the Triassic created a world that would have looked both beautiful and severe, with red floodplains, dusty basins, broad river systems, volcanic landscapes, and forests of plants that belonged to a much older botanical age. The animals of the Triassic were equally remarkable. This was not yet the classic age of dinosaurs. In fact, for much of the Triassic, dinosaurs were only minor members of the land ecosystems. The dominant animals were often other reptiles, especially archosaurs, the larger group that included the ancestors and relatives of crocodiles, dinosaurs, pterosaurs, and birds. Some archosaurs walked on all fours, some were armored, some were powerful predators, and some developed forms that seem almost like evolutionary experiments. Crocodile-line archosaurs were especially diverse and successful. There were large carnivores with deep skulls and sharp teeth, armored plant eaters, and strange forms that filled ecological roles dinosaurs would later occupy. In many Triassic environments, if one animal stood out as the ruler of the land, it was probably not a dinosaur. Dinosaurs were present, but they were still climbing slowly toward importance. Alongside these reptiles lived the synapsids, distant relatives of mammals. Earlier in Earth's history, synapsids had included many dominant land animals, but after the Permian extinction, their world had changed dramatically. Some survived into the Triassic as sturdy herbivores or small, active creatures. Among the most famous was Lystrosaurus, a beaked, barrel-bodied herbivore that became extraordinarily widespread in the early Triassic. Its success shows how empty and disrupted the world had become after extinction. A relatively simple, tough survivor could spread across huge areas and become one of the most common land animals on Earth. Other synapsids continued evolving in the background, giving rise to smaller, more mammal-like forms. These early mammal relatives were not yet the dominant furry animals of later ages. They were often small, nocturnal, and cautious, living beneath the feet of larger reptiles. Yet they carried within them another future, just as the early dinosaurs did. The Triassic was full of futures, only some of which would come true. Amphibians also remained important, especially in rivers, lakes, and wetlands. Some were enormous compared with modern frogs and salamanders, with broad, flat heads and powerful jaws. These animals were survivors of older lineages, living in watery environments where they could ambush fish and smaller creatures. The seas were recovering too. After the collapse of Permian marine ecosystems, new communities developed. Marine reptiles began to diversify, including early ichthyosaurs, which would later become sleek, dolphin-shaped hunters of the Mesozoic oceans. Fish, ammonoids, bivalves, and other marine organisms rebuilt complex food webs. Coral reefs slowly recovered, although not immediately in the forms seen before the extinction. The Triassic oceans, like the land, were places of rebuilding and replacement. In the skies, another extraordinary transformation was beginning. Pterosaurs, the first vertebrates to achieve powered flight, appeared during the late Triassic. They were not dinosaurs, but close relatives within the broader Archosaur family. Their wings were formed by a greatly elongated fourth finger supporting a membrane of skin and muscle. Early pterosaurs were often small, agile animals, likely feeding on insects, fish, or small vertebrates. Their appearance meant that vertebrates had now entered the air in a new way. Long before birds evolved from feathered dinosaurs, pterosaurs had already begun exploring the skies above Pangaea. On land, the first dinosaurs appeared in this dynamic and competitive world. They were small to medium-sized animals, often bipedal, with upright limbs held beneath the body. This posture made them efficient walkers and runners. Early forms, such as Eoraptor, Herrerasaurus, and other primitive dinosaurs, show that the group had already begun experimenting with different diets and body plans. Some were predators, some may have been omnivores, and others were moving toward herbivory. Still, they were not yet the main characters of the Triassic landscape. Their importance lay in their potential. Their bodies contained features that would later prove powerful: efficient movement, relatively rapid growth, adaptable feeding strategies, and anatomical flexibility. But in the Triassic, these advantages had not yet transformed them into rulers. They were survivors among many survivors. The Triassic world was also a world of instability. Climate changed across time and region. Some areas became wetter or drier. River systems shifted. Volcanic activity occurred in various places. As Pangaea began to experience the early forces that would eventually tear it apart, environments changed again. These pressures favored animals that could adapt, migrate, reproduce successfully, and exploit new opportunities. In such a world, extinction and evolution were closely connected. Groups that seemed powerful could disappear if conditions changed too quickly. Smaller or less dominant groups could suddenly expand when competitors declined. This is one of the central lessons of the Triassic. Success in one moment did not guarantee survival in the next. Near the end of the period, this lesson became dramatic. Around 201 million years ago, Massive volcanic eruptions associated with the opening of the Atlantic released huge amounts of carbon dioxide and other gases into the atmosphere. Climate disruption followed. Ecosystems were stressed, oceans were affected, and many groups of animals vanished. This Triassic-Jurassic extinction eliminated numerous large reptile competitors that had previously limited dinosaur expansion. Dinosaurs survived, and after the extinction, they spread into the vacant ecological spaces left behind. In this sense, the Triassic World was the testing ground of dinosaurs, not their empire. It shaped them, challenged them, and nearly hid them among other, more successful animals. But it also prepared the conditions for their rise. The Triassic was not a simple prelude. It was a full and complex world of its own, filled with strange reptiles, recovering forests, mammal ancestors, early flying pterosaurs, marine hunters, deserts, rivers, and evolutionary uncertainty. It was a world still healing from one catastrophe and moving unknowingly toward another. The first dinosaurs walked through this world as small figures in a vast, restless landscape. They did not yet dominate the planet, but they endured. And in the deep rhythm of Earth's history, endurance can be the beginning of greatness. Chapter 5. The Rise of Dinosaur Dominance. The rise of dinosaur dominance was not a sudden conquest, and it was not the result of one simple advantage. Dinosaurs did not appear on Earth as instant rulers, sweeping aside every rival through size, strength, or superior design. For tens of millions of years during the Triassic Period, they were only one group among many. They shared the land with crocodile-line archosaurs, large amphibians, mammal relatives, armored reptiles, and many strange animals that have no close modern equivalent. Some of these creatures were larger than early dinosaurs, more abundant than early dinosaurs, and in many environments far more important. If a traveler could have walked across Pangaea in the middle of the Triassic, dinosaurs might not have seemed like the future of life on land. They would have appeared as agile but modest animals, moving through river valleys and dry basins, surviving in ecosystems where other reptiles often held the most powerful positions. Yet by the beginning of the Jurassic Period, the situation had changed dramatically. Dinosaurs had become the dominant large land animals across much of the planet, and this dominance would continue for more than 130 million years. Their rise was one of the great evolutionary turning points in Earth's history, and it depended on anatomy, ecology, extinction, geography, and chance. One of the most important features that helped dinosaurs succeed was their posture. Unlike many reptiles with sprawling limbs extending out from the sides of the body, dinosaurs held their legs more directly beneath them. This upright stance made walking and running more efficient. It allowed the body to be supported like a bridge on vertical pillars, rather than dragged between side-splayed limbs. In practical terms, this meant dinosaurs could move with less wasted energy, maintain activity over longer distances, and develop more effective forms of locomotion. Early dinosaurs were often bipedal, balancing their bodies with long tails and moving on powerful hind limbs. This gave many of them speed and agility. Later dinosaur groups would use upright limbs in different ways, from the massive, column-like legs of sauropods to the sturdy stance of horned and armored dinosaurs. But the foundation was already present in the early forms. Efficient movement mattered in the changing landscapes of Pangaea, where food, water, and shelter could be separated by great distances, and where seasonal conditions often forced animals to travel. Another factor was growth. Fossil bones preserve microscopic evidence of how animals developed, and many dinosaurs seem to have grown relatively quickly compared with many other reptiles. Rapid growth could provide a major survival advantage. An animal that grows quickly spends less time as a small, vulnerable juvenile, reaches reproductive age sooner, and can respond more effectively to environmental pressures. This does not mean all dinosaurs had the same metabolism, or that they were simply warm-blooded in the same way as modern birds and mammals. Dinosaur physiology was likely varied and complex, but their growth patterns suggest that many of them were highly active animals, not slow, sluggish reptiles in the old-fashioned sense. They were capable of dynamic lives, and that dynamism may have helped them expand when opportunities appeared. Dinosaurs were also flexible. Early in their history, they began to divide into lineages with different diets and body plans. Theropods became mostly carnivorous, although some later forms would experiment with omnivory and herbivory. Sauropodomorphs began as smaller plant-eating or omnivorous animals and eventually evolved into the long-necked giants of the Jurassic. Ornithischians, at first small and relatively rare, would later produce stegosaurs, ankylosaurs, hadrosaurs, and ceratopsians. This early branching was essential. A group that can occupy many ecological roles has more chances to survive environmental change. If one lifestyle becomes difficult, another may continue. Dinosaurs were not locked into one narrow way of life. Their descendants could become hunters, browsers, grazers of low vegetation, high feeders, armored defenders, fast runners, herd animals, nest builders, display specialists, and eventually, flying birds. The seeds of this diversity were present during their early rise. Still, anatomy alone does not explain dinosaur dominance. The world itself had to change. During the late Triassic, many powerful competitors stood in the way of dinosaur expansion. Crocodile-line archosaurs were especially successful. Some were apex predators, others were armored herbivores, and many occupied roles that dinosaurs would later take over. As long as these groups thrived, dinosaurs remained limited in many ecosystems. Then, around 201 million years ago, Earth experienced the Triassic-Jurassic mass extinction. This event was connected to the breakup of Pangaea and enormous volcanic eruptions in the region that would become the Central Atlantic. These eruptions released vast quantities of carbon dioxide and other gases, contributing to global warming, ocean acidification, changes in rainfall, and widespread ecological stress. Many species disappeared. Entire groups of large reptiles declined or vanished. The extinction was destructive, but for surviving dinosaurs, it created opportunity. Ecological space opened on land. Predatory roles, herbivorous roles, and many regional habitats became available. Dinosaurs were among the groups able to pass through the crisis and expand afterward. In this way, their dominance was born not only from superiority, but from survival. They endured a world that destroyed many of their rivals. This is a recurring theme in evolution. The winners of history are often not the strongest in a simple sense, but those whose traits, locations, and circumstances allow them to survive catastrophe. After the extinction, dinosaurs entered the Jurassic Period in a transformed world. Their old competitors were reduced, and the continents were beginning to separate. The breakup of Pangaea created new coastlines, new climates, new river systems, and new patterns of isolation. Dinosaur populations spread, adapted, and diversified. Sauropodomorphs grew larger, eventually becoming some of the most massive animals ever to walk on land. Theropods increased in size and variety, producing large predators that ruled terrestrial food chains. Early ornithischians slowly expanded into new herbivorous roles. What had once been a relatively minor group became the defining land animals of the Mesozoic era. The scale of this transformation is remarkable. Within the Triassic, dinosaurs had been part of a crowded world. By the Jurassic, they were the central figures in many ecosystems. Their dominance did not mean they were the only animals that mattered. Mammal relatives still survived, usually in smaller forms. Crocodile relatives remained important, especially in rivers, lakes, and coastal environments. Pterosaurs ruled the skies, and marine reptiles occupied the oceans. But on land, especially among large-bodied animals, dinosaurs now held the commanding positions. They became the great herbivores shaping vegetation, and the great carnivores shaping prey behavior. Their nests, footprints, feeding trails, bones, and teeth became part of the geological record across the world. Their bodies influenced landscapes simply by living in them. A herd of large herbivorous dinosaurs could trample paths, spread seeds or spores indirectly, strip vegetation, and support entire communities of predators and scavengers. A large theropod could define the behavior of every smaller animal in its territory. Dominance is not just abundance, it is ecological influence. Dinosaurs had become animals around which ecosystems were organized. Yet their rise also reminds us that dominance is temporary in the deep history of Earth. No group rules forever. The same processes that lifted dinosaurs upward, climate change, extinction, shifting continents, new opportunities, would one day contribute to the end of most of them. But during the Jurassic and Cretaceous, their success was extraordinary. They adapted to deserts, forests, floodplains, coastal regions, polar environments, and island habitats. They evolved into tiny feathered hunters and immense, long-necked giants, into armored tanks and horned browsers, into swift runners and social herd animals. Their rise from small Triassic survivors to planetary icons was not a straight line, but a long unfolding of possibility. To understand dinosaur dominance, we must see it as the result of many forces working together. Their upright limbs made them efficient movers. Their growth and activity helped them compete. Their evolutionary flexibility allowed them to branch into many roles. Pangaea gave them room to spread. Extinction removed many rivals. The Jurassic World gave them space to expand. None of these factors alone tells the whole story, but together they explain how dinosaurs became the central land animals of their age. They did not conquer the world in a single dramatic moment. They inherited it after surviving hardship, adapting to opportunity, and moving through the open doors left by catastrophe. Their dominance began quietly, with small animals in the Triassic, and then grew into one of the longest and most spectacular reigns in the history of life. Chapter 6. The Jurassic Explosion. The Jurassic Period was the age when dinosaurs truly stepped into the center of Earth's great biological stage. After the hardships and uncertainty of the Triassic, after the rise of the first small dinosaurs and the extinction that removed many of their strongest rivals, the world changed into something broader, greener, and more open to dinosaur expansion. The Jurassic lasted from about 201 million to 145 million years ago, and during this time dinosaurs became larger, more diverse, and more deeply woven into the ecosystems of the planet than ever before. This was not simply a period when a few familiar giants appeared. It was a vast evolutionary expansion, a long wave of experimentation in size, shape, feeding, movement, defense, and behavior. The supercontinent Pangaea was beginning to break apart, and this geological transformation reshaped the world. Rifts opened between continents, new coastlines formed, seas flooded lowlands. Moisture patterns changed. Regions that had once been part of the dry interior of Pangaea became closer to water, and many landscapes grew more hospitable to large communities of plants and animals. The Jurassic World was still warm, with no great polar ice caps like those of today, but it was not uniform. There were forests, floodplains, river valleys, coastal plains, deserts, lakes, and volcanic regions. Ancient plants dominated the scenery. Conifers rose like dark green spires, cycads and bennettitalians gave many regions a palm-like appearance, ginkgos spread fan-shaped leaves, and ferns carpeted damp ground. Flowering plants had not yet transformed the world, and grasslands did not exist, So the great herbivorous dinosaurs fed on a vegetation very different from modern meadows or savannas. This plant world formed the foundation of the Jurassic Explosion, because as vegetation spread and diversified, herbivores found new opportunities, and predators followed the herbivores. Among the most spectacular results of this period was the rise of the sauropods, the long-necked giants that became some of the largest land animals in history. Their ancestors had existed earlier, but in the Jurassic, their bodies reached astonishing scale. Animals such as Diplodocus, Apatosaurus, Brachiosaurus, and their relatives developed long necks, long tails, massive bodies, and pillar-like legs. Their size was not just a curiosity, it was an ecological strategy. A long neck allowed an animal to reach huge volumes of vegetation without moving the entire body constantly. A large digestive system could process tough plant matter over long periods. Great size made adult sauropods difficult targets for predators. Their bodies became living machines for turning ancient vegetation into motion, growth, and reproduction. A herd of such animals moving across a Jurassic floodplain would have been one of the most impressive sights in the history of life. Immense bodies passing between conifers, tails swaying behind them, feet pressing deep tracks into mud that would sometimes harden and survive for millions of years. But the Jurassic was not only the age of long-necked giants, it was also a time of powerful predators. Theropod dinosaurs diversified into many forms, from smaller, agile hunters to massive carnivores capable of attacking large prey. Allosaurus became one of the best-known predators of the late Jurassic, with strong jaws, sharp teeth, grasping arms, and a body built for active hunting. Ceratosaurus, Torvosaurus, and other carnivores shared some of the same environments, suggesting that Jurassic predator communities could be complex, with different species hunting different prey or using different strategies. These animals were not mindless monsters. They were living predators, shaped by the same pressures that shape predators today. The need to find food, conserve energy, avoid injury, compete with rivals, and reproduce successfully. Hunting a giant sauropod was dangerous, and many predators may have focused on the young, the sick, the isolated, or the dead. Scavenging was likely important, as it is for many large carnivores. The presence of such predators would have influenced the behavior of herbivores, pushing them toward group living, vigilance, size, speed, armor, or defensive weapons. Another important group of Jurassic dinosaurs was the stegosaurs. These plant-eating dinosaurs, with their rows of plates and spiked tails, became iconic members of Jurassic ecosystems. Stegosaurus itself lived in the late Jurassic of North America, but its relatives appeared in other parts of the world. Their plates may have been used for display, species recognition, thermoregulation, or some combination of functions, while the tail spikes were clearly capable of defense. Stegosaurs were not giants on the scale of sauropods, but they represented another path in herbivore evolution. Instead of becoming extremely tall and massive, they developed distinctive defensive structures and specialized bodies suited to low browsing. Their presence shows how varied herbivorous dinosaurs had become. The Jurassic also saw the continued development of smaller dinosaurs, including early relatives of groups that would become more famous in the Cretaceous. Small ornithischians moved through the undergrowth, feeding on low plants and avoiding predators. Early feathered theropods and bird-like forms were beginning to reveal the deep connection between dinosaurs and birds, especially in the later Jurassic. Archaeopteryx, one of the most famous fossils ever found, lived around 150 million years ago in what is now Germany. It possessed feathers and wings, but also teeth, claws, and a long, bony tail. It was not a modern bird, but it was a remarkable glimpse of the transition from small theropod dinosaurs toward avian life. Its existence reminds us that the Jurassic Explosion was not only about giants. Some of the most important evolutionary changes were happening in small bodies, in feathers, in balance, in flight-related anatomy, and in the quiet beginnings of a lineage that still survives today. While dinosaurs dominated the land, they did not rule every realm. The Jurassic seas were home to marine reptiles such as ichthyosaurs and plesiosaurs, which were not dinosaurs, but lived alongside them in the same era. Ichthyosaurs moved through the water with streamlined bodies, hunting fish and squid-like animals. Plesiosaurs developed broad bodies, flippers, and in some forms, extremely long necks. Above the land and sea flew pterosaurs, also not dinosaurs, but close relatives within the archosaur world. They filled the skies long before birds became widespread. The Jurassic, therefore, was a complete Mesozoic world, with dinosaurs on land, pterosaurs in the air, marine reptiles in the oceans, early mammals in the shadows, and ancient plants forming the green architecture of the continents. The breakup of Pangaea continued to influence evolution throughout the Jurassic. As land masses separated, dinosaur populations became isolated from one another. Isolation encouraged regional differences. A dinosaur lineage in one part of the world might evolve in a different direction from its relatives elsewhere. At the same time, changing sea levels and shifting land connections sometimes allowed animals to disperse into new territories. This rhythm of separation and reconnection helped generate diversity. Fossils from North America, Europe, Africa, Asia, and other regions show that Jurassic dinosaurs were widespread, but not identical everywhere. Each region had its own ecological character, its own combination of plants, climates, predators, and herbivores. This makes the Jurassic feel less like one simple age and more like a living mosaic of worlds. The Jurassic Explosion was also an explosion of scale. Before this period, dinosaurs had already begun to grow and diversify, but during the Jurassic, the upper limits of land animal size were pushed to extraordinary levels. Sauropods especially transformed what was physically possible for terrestrial life. Their bones contained air spaces that helped lighten their skeletons. Their respiratory systems may have been highly efficient, and the reproductive strategy of laying eggs allowed them to avoid the impossible burden of carrying live young at gigantic size. These biological solutions helped make their enormous bodies possible. Yet their size also depended on environment. Enough plant material, enough space, and ecosystems capable of supporting them. The Jurassic provided these conditions in many places. By the end of the Jurassic, dinosaurs had become the defining animals of terrestrial Earth. They had expanded from their Triassic beginnings into giants, hunters, armored herbivores, small feathered forms, and countless regional species. Their world was rich, changing, and alive with evolutionary possibility. The Jurassic did not contain every famous dinosaur. Many icons, including Tyrannosaurus rex and Triceratops, belonged to the later Cretaceous. But the Jurassic was the period when the dinosaur age became unmistakable. It was when their dominance grew visible on a grand scale, when their bodies became monumental, when their ecosystems became complex, and when the deep future of birds began to take shape among small feathered theropods. The story of the Jurassic is the story of life expanding after crisis, of continents drifting apart, forests spreading across warm lands, and dinosaurs exploring the full range of what they could become. It was not merely an interval between two more famous moments. It was one of the greatest evolutionary flowerings in the history of land animals, a time when the age of dinosaurs truly became the age of dinosaurs. Chapter 7. Giant Plant Eaters. The giant plant-eating dinosaurs were among the most extraordinary animals ever to walk on land, not because they were simple, peaceful giants, but because their bodies represented some of the most ambitious experiments in the history of evolution. To become a huge herbivore is not merely to grow large. It means solving a whole series of biological problems: how to gather enough food, how to digest tough plants, how to support enormous weight, how to move efficiently, how to defend against predators, how to reproduce, and how to survive from a tiny hatchling into a creature that could outweigh a herd of modern elephants. During the Jurassic and Cretaceous periods, dinosaurs solved these problems in many different ways. Some became long-necked towers that could sweep through forests like living cranes. Others became armored fortresses, low browsers, horned defenders, or social herd animals. Together, they shaped the landscapes of the Mesozoic world. The most famous of all giant plant eaters were the sauropods, the long-necked dinosaurs that included animals such as Diplodocus, Apatosaurus, Brachiosaurus, Camarasaurus, and later giants like Argentinosaurus and Patagotitan. These animals pushed the size of land life to an extreme that has never been surpassed. A large sauropod could reach lengths greater than a blue whale, although it was usually much lighter, and some species may have weighed many tens of tons. Their bodies were built around a striking pattern: a small head, an extremely long neck, a massive barrel-like torso, 4 pillar-like legs, and a long tail. At first glance, this body plan seems almost impossible, but it was highly effective. A small head reduced the weight at the end of the neck. Air-filled spaces in many bones helped lighten the skeleton. Strong but relatively simple teeth allowed them to strip leaves, needles, and other plant material. They probably did not chew food in the detailed way that mammals do. Instead, many sauropods swallowed large amounts of vegetation and relied on enormous digestive systems to process it slowly. Their bodies were like great fermentation chambers, able to extract energy from plants that would have been difficult for smaller animals to use efficiently. The long neck of a sauropod was one of its greatest tools. It allowed the animal to reach food over a wide area while moving its heavy body as little as possible. Some sauropods may have fed high in trees, while others held their necks more horizontally, sweeping across broad feeding zones at medium or low heights. Different sauropod species likely divided their habitats by feeding at different levels or preferring different plants, which may have allowed several giant species to live in the same region without competing too directly. Their size also gave them protection. A fully grown sauropod was a dangerous target even for a large predator. A theropod might attack a juvenile, a sick adult, or a weakened individual. But a healthy adult sauropod could defend itself with sheer mass, powerful limbs, and sometimes a whip-like tail. Yet their lives began in a vulnerable form. Like other dinosaurs, sauropods laid eggs, and even the eggs of the largest species were not enormous compared with the adult body. This means that a baby sauropod emerged into the world tiny compared with its parents, facing a long and dangerous path to adulthood. Many probably died young, eaten by predators or lost to environmental pressures. Their reproductive strategy may have depended on producing many eggs, with only a small number surviving to maturity. Not all giant plant eaters became giants by growing tall. Stegosaurs followed a different path. These Jurassic herbivores had small heads, heavy bodies, strong limbs, and rows of plates rising along their backs. Their tails carried long spikes that could be used as weapons. Stegosaurus, the most famous member of this group, was not fast and did not have the towering height of a sauropod, but it was still a formidable animal. It likely fed on low vegetation such as ferns, cycads, and other plants near the ground. Its plates have inspired long debate. They may have helped with display, allowing individuals to recognize each other, attract mates, or intimidate rivals. They may also have played a role in temperature regulation, though this idea remains debated. Whatever their exact function, the plates made stegosaurs visually distinctive, while the tail spikes gave them a practical defense against predators. A large carnivore approaching a stegosaur had to risk serious injury from a sudden swing of the tail. In the Cretaceous, armored plant eaters became even more elaborate with the ankylosaurs. These dinosaurs were built like living tanks, with broad bodies, short, powerful limbs, bony armor embedded in the skin, and in some species, a heavy club at the end of the tail. Ankylosaurs did not need to outrun predators. Their strategy was resistance. Their backs were protected by plates, spikes, and knobs of bone. Some even had armored eyelids. Their wide bodies and low stance made them difficult to flip over or bite effectively. A predator facing an ankylosaur would have found few easy targets, and a tail club could break bone with a powerful strike. These animals fed close to the ground, cropping low vegetation and processing plants with relatively small teeth and strong digestive systems. They show that herbivory in dinosaurs was not passive. Eating plants could still require armor, strength, weapons, and complex survival strategies. Another major group of giant plant eaters was the ceratopsians, especially the horned dinosaurs of the late Cretaceous. Triceratops is the most famous example, with its large skull, 3 horns, and massive neck frill. Ceratopsians evolved from smaller ancestors into some of the most impressive herbivores of their time. Their beaks were excellent for cropping tough plants, and their teeth formed powerful slicing batteries that could process vegetation efficiently. Their horns and frills may have served multiple purposes: defense against predators, competition between individuals, display, species recognition, and sexual selection. A triceratops facing a Tyrannosaurus rex was not helpless prey. It was a powerful animal with a dangerous skull and a body built for resistance. Fossils suggest that horned dinosaurs lived in environments where encounters with large predators were real, and their anatomy reflects both feeding and defense. The hadrosaurs, or duck-billed dinosaurs, became some of the most successful herbivores of the late Cretaceous. Many were large, social animals with broad snouts, complex teeth, and powerful jaws capable of grinding plant material more effectively than earlier herbivores. Some hadrosaurs had elaborate crests, such as Parasaurolophus, whose long, hollow crest may have helped produce sounds, support display, or aid in species recognition. Hadrosaurs are especially important because fossil evidence gives us glimpses of their social lives. Bone beds suggest herds, nesting sites suggest reproductive colonies, and trackways suggest group movement. These dinosaurs were not merely background prey animals. They were highly successful, widespread, and adaptable herbivores that helped define many Cretaceous ecosystems. Giant plant eaters changed the world around them. By feeding, trampling, nesting, migrating, and dying, they influenced vegetation, soil, riverbanks, and food webs. Large herbivores today, such as elephants, can transform landscapes, and the largest dinosaurs likely had effects on an even greater scale. Sauropods moving through forests may have opened pathways and changed plant growth. Herds of hadrosaurs may have pressured certain plants heavily while spreading nutrients through their waste. Dead giants provided enormous resources for scavengers, insects, microbes, and predators. Even their footprints could become small basins that collected water or preserved traces of behavior in mud. The giant plant-eating dinosaurs were not simply animals living in the environment. They were forces within the environment. Their success also reveals the richness of Mesozoic plant life. Although there were no grasslands for most of the dinosaur age, there was abundant vegetation in many habitats. conifers, cycads, ginkgos, ferns, horsetails, and later flowering plants provided the energy base for immense bodies and complex ecosystems. Herbivorous dinosaurs evolved again and again into forms capable of using these resources. Some relied on size, some on armor, some on teeth, some on herds, some on height, and some on weapons. The phrase plant eater can sound gentle, but the reality was far more dramatic. These animals were engineers, survivors, competitors, parents, migrants, and defenders. They lived under the constant pressure of predation and environmental change, yet they became some of the most successful creatures of their age. To imagine the dinosaur world without them would be impossible, because they were the foundation on which many ecosystems rested. The great predators depended on them. The landscapes were shaped by them. The fossil record is filled with their bones, tracks, nests, teeth, armor, and eggs. From the towering sauropods of the Jurassic to the horned and duck-billed herds of the Cretaceous, the giant plant eaters show that the age of dinosaurs was not only an age of hunters, it was also an age of immense herbivores, animals that turned ancient sunlight stored in plants into flesh, movement, defense, and life on a scale the land had never seen before and has never seen again. Chapter 8. Predators of the Jurassic. The Jurassic World was not only a world of giants peacefully feeding among ancient forests. It was also a world of hunters, scavengers, ambushes, injuries, competition, and constant alertness. Wherever great plant-eating dinosaurs lived, predators followed, and during the Jurassic Period, the meat-eating dinosaurs became more varied, more powerful, and more important than ever before. These predators belonged mostly to a group called theropods, the same great branch of dinosaurs that would much later give rise to birds. In the Jurassic, theropods ranged from relatively small, agile hunters to enormous carnivores capable of challenging some of the largest animals on land. They were not all the same, and they did not all hunt in the same way. Some had deep skulls and strong bites. Others had lighter bodies and speed. Some may have specialized in smaller prey, while others could attack juvenile sauropods, stegosaurs, or weakened adults. To understand Jurassic predators, we must imagine them not as movie monsters roaring constantly, but as living animals shaped by hunger, risk, instinct, anatomy, and opportunity. A predator's life is dangerous. Every hunt costs energy. Every attack can lead to injury. A broken jaw, damaged leg, or infected wound could mean death. Because of this, Jurassic carnivores probably behaved with the same practical caution seen in many modern predators. They hunted when they could, scavenged when possible, avoided unnecessary danger, and selected vulnerable targets when available. The most famous Jurassic predator is Allosaurus, one of the defining carnivores of the late Jurassic. Fossils of Allosaurus are especially well known from North America, particularly from the Morrison Formation, a rich fossil-bearing rock unit that has preserved an extraordinary picture of Jurassic life. Allosaurus was large, often reaching around 8 to 10 meters in length, though some individuals may have been bigger. It had a strong but relatively lightweight skull, sharp, serrated teeth, powerful hind limbs, a long, balancing tail, and 3-fingered hands with claws. Its eyes faced somewhat forward, giving it useful depth perception for judging distance during attacks. For a long time, Allosaurus was imagined as a simple giant killer, but its anatomy suggests a more complex predator. Its skull was not built exactly like that of later Tyrannosaurs, which had crushing bites and massive bone-breaking jaws. Allosaurus may have used a different feeding strategy, perhaps slashing and tearing with its teeth, using its neck and body to drive attacks, and relying on repeated wounds rather than one overwhelming bite. It likely hunted a wide range of prey, from smaller ornithischians to young sauropods, and it almost certainly scavenged when it found carcasses. In a landscape inhabited by massive herbivores, a dead sauropod would have been a feast of unbelievable scale, attracting predators from far around. Allosaurus did not live alone in the Jurassic predator world. It shared ecosystems with other large theropods, such as Ceratosaurus and Torvosaurus. Ceratosaurus was slightly smaller than the largest Allosaurus in many cases, but it was a formidable carnivore with a distinctive horn on its snout, bony ridges above the eyes, and blade-like teeth. Its body was powerful, and some features suggest it may have had a somewhat different ecological role from Allosaurus. Perhaps it hunted in different habitats, preferred different prey, or relied more on ambush. Torvosaurus, on the other hand, was one of the largest Jurassic theropods, with a massive skull, strong jaws, and large teeth. The presence of several large predators in the same broad environments raises an important question. How did they avoid direct competition? The answer may lie in ecological separation. Modern ecosystems often contain multiple predators that divide resources by prey size, hunting method, habitat, or time of activity. Lions, leopards, hyenas, wild dogs, and cheetahs can live in overlapping regions because they do not all use the environment in exactly the same way. Something similar may have happened in the Jurassic. One predator might have preferred riverine areas, another open floodplains. One might have focused on carcasses and large prey, another on smaller animals. One might have hunted with bursts of speed, another through ambush. Fossils cannot always reveal these details clearly, but the variety of theropod bodies suggests that Jurassic predator communities were not simple. The prey they hunted were equally impressive. Jurassic herbivores included sauropods such as Diplodocus, Apatosaurus, Camarasaurus, and Brachiosaurus, as well as stegosaurs and smaller plant eaters. Adult sauropods were enormous, and attacking one would have been extremely risky. Even without horns or claws, a giant sauropod had mass as its greatest defense. A kick, a tail strike, or simply being crushed beneath a falling body could kill or cripple a predator. Because of this, predators may have more often targeted juveniles. Young sauropods, though still large compared with many animals, would have been far easier to attack than adults. Eggs and hatchlings may also have attracted smaller predators, scavengers, and opportunistic feeders. Stegosaurs presented a different challenge. They were not as large as the biggest sauropods, but they carried dangerous weapons. The spiked tail of Stegosaurus, sometimes called a thagomizer, could deliver serious injuries. Fossil evidence from injured predator bones suggests that such weapons were not decorative. A Jurassic hunter approaching a stegosaur had to calculate risk, even if only through instinct. One badly placed strike from a tail spike could pierce muscle, damage bone, or cause a wound that later became infected. This constant contest between predator and prey helped shape both sides. Predators evolved teeth, claws, senses, speed, and tactics. Prey evolved size, armor, group behavior, defensive weapons, and vigilance. The Jurassic was therefore not a static world, but an evolutionary arms race unfolding over millions of years. Smaller predators also played important roles. Not every theropod was a giant. Many Jurassic carnivores were medium-sized or small animals that hunted lizards, early mammals, insects, young dinosaurs, and other small prey. Some were fast and bird-like in their movements. These smaller theropods are especially important because they show the evolutionary path toward feathers, agility, and eventually birds. In the late Jurassic, animals close to the origin of birds were already developing complex, feathered bodies. Archaeopteryx, though not a large predator, was part of this wider theropod world. It had teeth, claws, a long bony tail, and feathers. Its existence reminds us that the predatory dinosaurs of the Jurassic were not only gigantic hunters. Some were small, quick, alert animals, moving through trees, along the ground, or across coastal environments, catching insects and small vertebrates. In the long view of evolution, these small predators were just as important as the giants, because their lineage would survive the later extinction in the form of birds. The senses of Jurassic predators were crucial to their success. A meat-eating dinosaur needed good vision to track movement, judge distance, and recognize prey. Smell may also have been important, especially for detecting carcasses. Hearing could help locate animals hidden in vegetation or moving nearby. Balance and coordination were essential for active hunting, particularly in bipedal animals whose bodies depended on long tails and powerful hind limbs for stability. Theropod skulls show that these animals were not dull or primitive. Their brains were not mammalian in structure, but they were suited to the demands of predatory life. They had to navigate territories, recognize threats, compete with rivals, locate food, and respond quickly to moving prey. The Jurassic predator lived by attention. The world around it was full of signals: footprints in mud, the scent of blood, alarm movements among herbivores, distant calls, fresh carcasses, broken vegetation, and the presence of rival carnivores. Social behavior among Jurassic predators remains a difficult question. Some fossil sites have preserved multiple individuals of the same species, leading to speculation about group hunting or social living. But evidence must be treated carefully. Animals can gather in one place for many reasons: drought, flood, trapped prey, carcasses, nesting areas, or simple accidents of preservation. Allosaurus, for example, has sometimes been imagined as a pack hunter, but it is not certain that it hunted in coordinated groups like wolves. It may have been solitary, loosely social, or opportunistically gathered around food sources like crocodiles or Komodo dragons. Even if some theropods tolerated each other at times, that does not mean they cooperated in a highly organized way. Still, the possibility of social interaction cannot be dismissed entirely. Modern reptiles, birds, and mammals show a wide range of behaviors, and extinct dinosaurs likely did too. Some may have defended territories. Some may have competed violently for mates or carcasses. Some may have cared for young. Some may have used display features, sounds, or body postures to communicate. Predation was not only about killing. It was part of a larger life cycle that included growth, reproduction, rivalry, and survival. The Jurassic predators also left their mark through trace fossils. Footprints can show how theropods moved across mudflats, riverbanks, and coastal plains. Trackways reveal stride length, speed estimates, group movement in some cases, and interactions with landscapes. Bite marks on bones show feeding behavior. Broken and healed bones reveal injuries survived by predators or prey. Teeth shed during feeding are sometimes found near herbivore remains, suggesting moments when carnivores consumed carcasses. These traces are powerful because they capture behavior, not just anatomy. A skeleton tells us what an animal was built like. A trackway or bite mark tells us something it did. Through these clues, the Jurassic becomes more alive. A predator walking along a shoreline, a carcass being torn open, a wounded animal surviving an attack, a small theropod crossing wet mud and leaving delicate three-toed prints behind. The predators of the Jurassic were essential to the balance of their ecosystems. They controlled prey populations, removed weak and dead animals, competed with one another, and drove evolutionary change in herbivores. Their presence shaped the behavior of every animal around them. A young sauropod had to grow quickly because predators existed. A stegosaur's tail spikes mattered because predators existed. Herd behavior, nesting choices, migration routes, and vigilance were all influenced by the risk of being eaten. At the same time, predators depended entirely on the abundance of herbivores and smaller animals. They were powerful, but they were not independent. They were tied to the plant world through the bodies of their prey. Ancient sunlight fed conifers and ferns. Herbivores ate those plants. Predators ate the herbivores. In this way, even the sharpest tooth of Allosaurus was connected to the green foundation of the Jurassic landscape. The story of Jurassic predators is therefore not just a story of violence. It is a story of ecology, adaptation, and deep time. These animals were magnificent because they were part of a living system. They moved through warm floodplains, conifer forests, dry basins, river edges, and coastal environments. They faced hunger, injury, competition, and opportunity. Some became giants capable of standing at the top of food chains. Others remained small and quick, following evolutionary paths that would eventually lead toward birds. Together, they made the Jurassic World dynamic and dangerous. Without them, the giant plant eaters would not have evolved in the same way, and the ecosystems of the dinosaur age would have been far less complex. The predators of the Jurassic remind us that the age of dinosaurs was not only an age of size, but an age of tension between hunter and hunted, risk and reward, strength and vulnerability, life and death. Chapter 9. The Cretaceous World. The Cretaceous World was the final and longest chapter of the dinosaur age, lasting from about 145 million to 66 million years ago, and it was a time of enormous change. If the Jurassic was the age when dinosaurs became truly dominant, the Cretaceous was the age when their world became richer, more divided, more colorful, and more complex. By this time, the supercontinent Pangaea had already begun to break apart, but during the Cretaceous, this process continued on a grand scale. Continents drifted farther from one another, oceans widened, new coastlines appeared, and shallow seas spread across parts of the land. The map of the planet began to look more familiar, though it was still very different from the modern world. North America was split for much of the period by a great inland sea. South America and Africa moved apart as the Atlantic Ocean expanded. India became an isolated island continent drifting northward toward Asia. Australia remained connected to Antarctica for much of the period, and many land masses experienced their own separate evolutionary stories. This geographical division was one of the great engines of Cretaceous diversity. Dinosaur populations that had once been able to spread across connected lands became isolated by oceans, mountains, deserts, and changing climates. Over millions of years, isolation produced regional worlds, each with its own dinosaurs, plants, predators, and herbivores. The Cretaceous was not one single dinosaur landscape. It was a mosaic of ancient worlds, from humid forests and coastal plains to dry uplands, polar woodlands, river deltas, islands, and inland basins. The climate was generally warm, with high sea levels and no permanent polar ice caps like those of today. But that does not mean every place was tropical. There were strong regional differences, seasonal changes, storms, droughts, and polar regions where dinosaurs lived through long periods of summer light and winter darkness. One of the most important transformations of the Cretaceous was the rise of flowering plants. For most of the earlier dinosaur age, the plant world had been dominated by conifers, cycads, ginkgos, ferns, horsetails, and other ancient groups. During the Cretaceous, flowering plants, or angiosperms, began to spread and diversify. At first, they may have been relatively modest parts of the environment, but over time, they became increasingly important. Their flowers, fruits, leaves, and rapid life cycles changed ecosystems in profound ways. They created new food sources for insects, which in turn affected birds, small dinosaurs, mammals, and other animals. They altered forests, riverbanks, and open habitats. They helped shape the evolution of pollinators and herbivores. The spread of flowering plants did not instantly replace older vegetation, and many ancient plant groups remained important, but it added a new layer of complexity to the dinosaur world. By the late Cretaceous, landscapes could include a mixture of conifers, ferns, cycads, and flowering shrubs or trees. This botanical revolution influenced the animals that lived among them, especially herbivorous dinosaurs that were evolving increasingly specialized jaws, teeth, and feeding strategies. Among the most successful herbivores of the Cretaceous were the hadrosaurs, often called duck-billed dinosaurs. These animals became widespread and diverse, especially in the late Cretaceous. Their broad mouths helped them crop vegetation, and their remarkable dental batteries allowed them to grind and process plants efficiently. Some hadrosaurs, such as Parasaurolophus and Corythosaurus, carried elaborate hollow crests that may have helped produce sound, display identity, attract mates, or distinguish species. Hadrosaurs were not simple prey animals waiting for predators. They were among the great evolutionary successes of their time, living in herds, nesting in colonies, migrating across landscapes, and adapting to different environments. Their fossils are found in huge numbers in some regions, suggesting that they formed a major part of Cretaceous ecosystems. Alongside them were ceratopsians, the horned dinosaurs, which became especially prominent in North America and Asia. Triceratops, Styracosaurus, Protoceratops, and their relatives evolved powerful beaks, complex teeth, large skulls, horns, and frills. These features served not only for defense, but probably also for display, recognition, and competition. In the Cretaceous world, the head of a dinosaur could become a visual signal as important as a weapon. Frills, crests, horns, domes, and feathers all suggest that appearance mattered deeply in dinosaur life. Dinosaurs were not gray, silent, identical reptiles. They were animals of shapes, signals, colors, sounds, and behaviors that we can only partly reconstruct. Armored dinosaurs also flourished in the Cretaceous. Ankylosaurs became heavily protected herbivores with bodies covered in bony armor, and some developed massive tail clubs capable of delivering powerful blows. Nodosaurs, close relatives of ankylosaurs, often lacked tail clubs but carried impressive armor and shoulder spikes. These low, broad, plant-eating dinosaurs show another path to survival. Instead of running from predators or gathering in massive herds, they turned their bodies into defensive fortresses. The Cretaceous was also the age of some of the most famous predators in Earth's history. Tyrannosaurs rose from smaller, earlier ancestors into gigantic apex predators by the late Cretaceous. Tyrannosaurus rex, living near the very end of the period, was one of the largest land predators ever known, with a massive skull, bone-crushing bite, powerful legs, keen senses, and teeth built not simply to slice flesh, but to puncture and break. In other regions, different predators ruled. In South America, large abelosaurids, such as Carnotaurus, developed short, deep skulls, tiny arms, and powerful hind limbs. In Africa and South America, earlier Cretaceous ecosystems included enormous Carcharodontosaurids and Spinosaurids, including Spinosaurus, a strange predator associated with aquatic environments and fish-eating adaptations. Predator communities varied by continent and time. There was no single universal ruler of the Cretaceous. Each region had its own hunters, each shaped by local prey, climate, geography, and evolutionary history. Smaller theropods also became increasingly important. Dromaeosaurs, troodontids, oviraptorosaurs, ornithomimosaurs, and many other groups filled diverse ecological roles. Some were swift runners, Some were feathered hunters. Some had beaks. Some ate eggs, plants, insects, small animals, or mixed diets. The closer scientists look at the Cretaceous, the less it appears to be a simple world of giant monsters, and the more it appears as a detailed, living system full of specialization. Feathers were especially important. By the Cretaceous, many theropods had feathers or feather-like coverings, used not only for flight, but also for insulation, display, brooding eggs, and communication. Birds themselves, descended from small feathered theropods, diversified during this period. They shared the skies with pterosaurs, which also continued to evolve into remarkable forms, including some of the largest flying animals ever known. The oceans were filled with marine reptiles such as mosasaurs, plesiosaurs, and sea turtles, while ammonites, fish, sharks, and countless invertebrates populated the seas. Mammals remained mostly small compared with dinosaurs, but they were not irrelevant. They evolved into many forms, including insect eaters, climbers, burrowers, swimmers, and even animals capable of eating small dinosaurs. They lived in the margins of the dinosaur world, but they were quietly diversifying, carrying another future within them. The Cretaceous world was therefore a planet of abundance and tension. It was beautiful, warm, and biologically rich, but it was also unstable. Sea levels rose and fell, volcanoes erupted, continents continued to drift, climates shifted, ecosystems changed as flowering plants spread and older plant communities adjusted. Dinosaurs responded with extraordinary variety. Some became more specialized, others more widespread. Some grew gigantic, others remained small and agile. Some developed weapons, others armor, others speed, others complex teeth, others feathers and display structures. By the late Cretaceous, dinosaurs had reached one of the highest points of their diversity and ecological sophistication. This is part of what makes their ending so powerful. The non-bird dinosaurs did not disappear because they were old, weak, or already doomed in a simple sense. Many groups were still successful, still evolving, still deeply integrated into their environments. The Cretaceous was not merely the decline before extinction. It was a final flourishing. Across the world, hadrosaur herds moved through river valleys. Tyrannosaurs hunted along floodplains. Horned dinosaurs faced rivals and predators. Armored dinosaurs browsed close to the ground. Small feathered theropods darted through vegetation. Birds flew among trees. Pterosaurs crossed inland seas. And flowering plants quietly changed the future of terrestrial life. The Cretaceous world was the last great world of the non-bird dinosaurs, and perhaps the most complex one they ever knew. It contained the end of their reign, but before that end came richness, invention, beauty, and a planet filled with forms of life that had been more than 150 million years in the making. Chapter 10: Tyrannosaurs and Apex Predators. Among all the predators that ever walked the earth, few have captured the human imagination as powerfully as the tyrannosaurs. Their name alone suggests domination. Tyrant lizards, animals built around massive skulls, crushing jaws, powerful legs, and the role of top predator in some of the last great ecosystems of the dinosaur age. Yet the story of tyrannosaurs is more interesting than the image of one famous giant. Tyrannosaurus rex was not the beginning of the group, but the final and most spectacular expression of a long evolutionary history. Tyrannosaurs began as relatively small theropods, living in the shadow of other carnivorous dinosaurs. Their earliest relatives were not gigantic rulers of the land. Some were agile, lightly built predators, perhaps covered in simple feathers or feather-like filaments, hunting small animals in Jurassic and early Cretaceous ecosystems. For much of their history, tyrannosaurs were not the largest predators around. Other groups, such as Allosaurids, Carcharodontosaurids, and Megalosauroids, often occupied the highest predatory roles. The rise of tyrannosaurs to apex status happened gradually, especially during the late Cretaceous, as older predator groups declined in many northern continents and tyrannosaurs expanded into the open ecological space. Their success was not based on size alone. It was based on a combination of senses, growth, bite force, movement, and adaptation to the prey animals of their time. The most famous tyrannosaur, Tyrannosaurus rex, lived near the very end of the Cretaceous period, about 68 to 66 million years ago, in what is now Western North America. It shared its world with animals such as Triceratops, Edmontosaurus, Ankylosaurus, Pachycephalosaurus, and many smaller dinosaurs, mammals, reptiles, birds, and insects. This was not a primitive swamp full of monsters, but a complex world of floodplains, forests, rivers, coastal lowlands, seasonal changes, and diverse plant life. In that world, Tyrannosaurus rex stood at the top of the food chain. It could reach more than 12 meters in length, stand several meters tall at the hips, and weigh several tons. But its most remarkable feature was its head. The skull of Tyrannosaurus rex was enormous, deep, and heavily reinforced, with large openings that reduced weight while preserving strength. Its teeth were not thin, slicing blades like those of many earlier theropods. They were thick, curved, and robust, shaped more like lethal railroad spikes than knives. These teeth could puncture deeply, grip flesh, crush bone, and withstand tremendous stress. The bite of Tyrannosaurus rex was one of the most powerful bites known among land animals, and this changed the way it fed. Unlike some predators that mainly sliced meat from a carcass, Tyrannosaurus could bite through bone and consume parts of prey that many other carnivores might have left behind. Fossil bones with deep tyrannosaur tooth marks show that these animals could break, scrape, and crush skeletal material. This made them efficient feeders as well as terrifying hunters. A large carcass in the Cretaceous would not have lasted long if tyrannosaurs discovered it. Whether they killed the animal themselves or arrived later as scavengers, they could extract enormous nutritional value from it. The old debate over whether Tyrannosaurus rex was a hunter or scavenger is now often seen as too simple. Most large carnivores do both. Lions hunt, but also steal kills and scavenge. Hyenas hunt more than their reputation suggests, but also feed on carcasses. Bears, wolves, crocodiles, eagles, and many other predators take food wherever they can find it. Tyrannosaurus rex was almost certainly no different. Its body was capable of active predation, and its senses were highly developed. But it would not ignore a dead dinosaur lying in the open. In nature, free food is too valuable to waste. The more interesting question is not hunter or scavenger, but how it hunted, what it preferred, how often it succeeded, and how it interacted with other predators and prey. Tyrannosaurus had excellent senses. Its skull suggests a strong sense of smell, useful for detecting carcasses, tracking prey, or recognizing territories and other individuals. Its eyes faced forward enough to provide good depth perception, important for judging distance during movement and attack. Its inner ear and brain structure suggest balance and coordination suited to an active animal. This was not a clumsy giant stumbling through the Cretaceous. It was a highly specialized predator. Its legs were powerful, though scientists continue to debate exactly how fast an adult Tyrannosaurus could run. It probably was not a lightning-fast sprinter in the exaggerated sense of some older depictions, because an animal of such mass risked severe injury from a fall. But it did not need to run like a cheetah. It needed to move efficiently, accelerate enough for short pursuits, ambush when possible, and overpower large prey once close. Younger tyrannosaurs may have been faster and more lightly built, perhaps occupying different predatory roles from adults. This is an important point. A juvenile Tyrannosaurus was not simply a miniature adult. It had a slimmer body, longer legs relative to size, and a more agile build. As it grew, it transformed from a fast, blade-toothed hunter into a massive, bone-crushing giant. This means one species could occupy different ecological roles at different life stages, reducing competition between young and adult individuals. Other tyrannosaurs show the diversity of the group. Albertosaurus and Gorgosaurus lived earlier than Tyrannosaurus rex in North America and were generally more slender, though still formidable predators. Daspletosaurus was more robust and may represent an important step toward the massive skull design of T. rex. In Asia, Tarbosaurus occupied a similar apex role, while smaller tyrannosauroids show the earlier stages of the lineage. Some early tyrannosauroids likely had feathers, and it is possible that certain larger species retained some feathering, especially as juveniles or in particular body regions, though the exact appearance of the largest tyrannosaurs remains debated. What is clear is that tyrannosaurs were not naked movie monsters in the simple sense. They belonged to the theropod branch, deeply connected to birds, feathers, display, rapid growth, and complex behavior. As apex predators, tyrannosaurs shaped the behavior of the animals around them. A herd of hadrosaurs moving across a floodplain would have lived with the constant danger of attack. A triceratops was powerful, armed, and dangerous, but even it would have been vulnerable if young, old, isolated, injured, or caught in a bad position. Ankylosaurus, covered in armor and equipped with a tail club, represented a very different challenge. For a tyrannosaur, every prey animal demanded a different calculation. Attack the wrong individual, and the predator could be wounded or killed. A horn thrust, a tail club strike, a kick, or a fall during a struggle could end its life. Apex predators are powerful, but they are never invincible. Their survival depends on judgment, patience, opportunity, and sometimes luck. The Cretaceous world contained other apex predators beyond tyrannosaurs. In South America, abelisaurids such as Carnotaurus developed deep skulls, strong necks, reduced arms, and powerful hind limbs. In earlier parts of the Cretaceous, enormous Carcharodontosaurids such as Giganotosaurus and Carcharodontosaurus rivaled or exceeded tyrannosaurs in length, with skulls full of blade-like teeth adapted for slicing flesh. Spinosaurus from North Africa followed a stranger path, with a long, crocodile-like snout, conical teeth, powerful forelimbs, a tall sail on its back, and adaptations suggesting a close relationship with aquatic environments and fish-rich ecosystems. These predators remind us that there was no single model for being an apex carnivore. One lineage evolved crushing jaws, another slicing teeth, another semi-aquatic habits, another speed or ambush. Each apex predator was shaped by its environment and prey. Tyrannosaurs became the supreme predators mainly in the northern continents during the late Cretaceous, but elsewhere, other hunters held similar power. Their world was not ruled by one monster, but by many local kings. What makes tyrannosaurs especially fascinating is the combination of brute strength and biological sophistication. They grew rapidly, sensed their world keenly, changed dramatically as they aged, and interacted with prey animals that were themselves highly evolved. They lived at the very end of the non-bird dinosaur era, when ecosystems were rich with flowering plants, complex herbivore communities, birds, mammals, insects, pterosaurs, and reptiles. Tyrannosaurus rex did not live in an ancient failure of a world. It lived in a thriving world near its final moment. Its reign was short in geological terms, but unforgettable. When the asteroid struck at the end of the Cretaceous, the great Tyrannosaurs disappeared with the other non-bird dinosaurs. Their bones remained buried in floodplains and rock layers, waiting tens of millions of years to be found. Today, they stand as symbols of prehistoric power. But their true story is deeper than power alone. They were not monsters. They were animals. Growing, hunting, scavenging, competing, mating, aging, surviving, and finally, vanishing. The Tyrannosaurs show us the peak of predatory dinosaur evolution, but also the fragility of even the greatest rulers in Earth's history. Chapter 11. Horned and armored dinosaurs. Among the most impressive plant-eating dinosaurs of the Cretaceous world were the horned and armored dinosaurs, animals that turned defense into an evolutionary art form. They were not the biggest dinosaurs that ever lived, and they were not predators, but they developed some of the most memorable bodies in the entire history of life. Their skulls became shields and signals, their backs became walls of bone, their tails became clubs or weapons. Their bodies tell a story of survival in landscapes filled with danger, especially in a world where powerful predators such as tyrannosaurs, abelisaurids, and other theropods could threaten even large herbivores. To eat plants in the dinosaur age was not to live peacefully without struggle. Herbivores had to find food, compete for mates, protect their young, survive droughts and floods, and avoid becoming prey. Horned and armored dinosaurs show that plant eaters could be just as dramatic, specialized, and formidable as the carnivores that hunted them. The horned dinosaurs are known as ceratopsians, a group that began with relatively small, often lightly built animals, and eventually produced some of the most powerful herbivores of the late Cretaceous. Early ceratopsians, such as Psittacosaurus, looked very different from Triceratops. Psittacosaurus was a small beaked dinosaur, often moving on two legs or using a mixed posture, with a parrot-like mouth suited for cropping plants. It did not yet have the huge horns and frill of later relatives, but it already possessed the basic feeding equipment that would become important in the group: a strong beak, teeth for processing vegetation, and a skull adapted to plant eating. Over millions of years, ceratopsians became larger, more quadrupedal, and more heavily ornamented. In Asia and North America, they evolved into animals with massive heads, broad frills, cheek teeth arranged for slicing tough plants, and in many species, horns above the eyes or nose. By the late Cretaceous, ceratopsians had become some of the dominant herbivores in certain ecosystems. Triceratops is the most famous of them all, living near the very end of the Cretaceous, around the same time as Tyrannosaurus rex. It had 3 horns, a large bony frill, a powerful body, and a skull that could grow to extraordinary size. For a long time, people imagined Triceratops mainly as the natural enemy of Tyrannosaurus, locked in endless battles on prehistoric floodplains. There is some truth behind the drama. These animals did live in the same environments, and fossil evidence shows that tyrannosaurs bit ceratopsian bones. But Triceratops was more than prey and more than a defensive machine. Its horns and frill likely served several purposes. They could help defend against predators, but they may also have been used in contests between individuals, in attracting mates, in recognizing members of the same species, and in displaying age, health, or strength. Many modern animals carry weapons that are also signals. Deer antlers, bison horns, rhinoceros horns, and the tusks of some mammals are used not only against predators, but also in competition and communication. Ceratopsians may have lived in a similarly visual world, where the shape of the skull mattered socially as well as practically. Their frills were not all the same. Some species had long spikes around the edges, others had broad shields, hooks, openings, ridges, or
were elaborate shapes that varied from one species to another. Styracosaurus carried dramatic spikes from its frill. Centrosaurus had a large nasal horn and a shorter frill. Protoceratops, a smaller Asian relative, lacked the enormous horns of Triceratops, but had a noticeable frill and strong beak.
This variety suggests that ceratopsian evolution was deeply tied to display and species recognition. In a world where several related herbivores might share similar environments, visual differences could help animals identify their own kind. Color, which rarely fossilizes directly, may have made these structures even more striking. A ceratopsian frill covered in skin could have carried patterns, flushes of blood, scars, or seasonal changes that are lost to us now. The fossils preserve the architecture, but the living animal was probably more vivid than bone alone can show. Their feeding was equally important. Ceratopsians had strong beaks for cutting vegetation and dental batteries for slicing and processing tough plants. They may have fed on cycads, palms, ferns, conifers, and later flowering plants, depending on region and period. Their heads were heavy, but powerful necks and shoulders supported them. They were not fast like some smaller dinosaurs, but they were sturdy, muscular, and difficult to attack. A large ceratopsian facing a predator could lower its head, present its horns, and become a serious threat. A tyrannosaur attacking a healthy adult triceratops would have faced real danger. The armored dinosaurs followed a different strategy. Instead of developing giant horned skulls, they transformed their backs, sides, and tails into defensive structures. The most famous armored dinosaurs are ankylosaurs, broad-bodied, four-legged herbivores covered in bony plates called osteoderms. These plates were embedded in the skin and formed armor across the neck, back, flanks, and sometimes even parts of the head. Some ankylosaurs, such as Ankylosaurus itself, developed a heavy bony club at the end of the tail. This tail club was not decorative. Built from fused bones and powered by strong tail muscles, it could have delivered devastating blows. A strike to the leg of a predator might break bone or cause injury serious enough to end a hunt. Ankylosaurs were low to the ground, wide and heavily protected. They were not designed for speed. Their defense was patience, armor, and impact. A predator looking at an adult ankylosaur would find very few safe places to bite. The back was armored, the skull was reinforced, the sides were protected, and the tail could swing as a weapon. Even turning the animal over would have been difficult because of its broad, heavy body. In this sense, ankylosaurs were among the closest things the dinosaur world produced to living tanks. Their relatives, the nodosaurs, often lacked tail clubs but carried impressive armor, shoulder spikes, and long defensive projections. Some nodosaurs may have looked even more spiny than ankylosaurs, with large spikes along the sides of the body that made them difficult to approach. One remarkable fossil of the nodosaur, Borealopelta, preserved not just bones, but armor arrangement and traces of pigmentation, giving scientists a rare glimpse of how such an animal may have appeared in life. Evidence suggests it had countershading, with a darker upper body and lighter underside, a pattern common in many animals today. This is fascinating because it implies that even a heavily armored dinosaur may still have benefited from camouflage, perhaps because predators remained dangerous, especially when the animal was young or vulnerable. Armored dinosaurs were herbivores, usually feeding close to the ground. Their teeth were relatively small compared with the elaborate dental batteries of hadrosaurs or ceratopsians, so they probably relied heavily on their digestive systems to process plant material. They may have eaten ferns, low shrubs, cycads, and other vegetation near the forest floor. Their wide bodies would have contained large guts capable of breaking down tough plants slowly. Like sauropods, they turned ancient vegetation into mass, but in a very different form, not height and reach, but compact strength and protection. Horned and armored dinosaurs remind us that evolution does not produce one perfect solution. It produces many workable solutions, shaped by environment, ancestry, and pressure. A sauropod survived through enormous size. A hadrosaur survived through efficient feeding and often herd life. A ceratopsian survived through powerful jaws, social signals, horns, and frills. An ankylosaur survived through armor and a weaponized tail. Each of these strategies worked for millions of years. They also shaped predator evolution. A carnivore living among horned and armored dinosaurs had to be powerful, careful, and opportunistic. It might target juveniles rather than adults, attack from the side or rear, wait for weakness, scavenge carcasses, or avoid the most dangerous individuals entirely. The relationship between predator and prey was never simple. It was a long, evolutionary conversation written in teeth, horns, armor, scars, and healed wounds. These dinosaurs also had social lives that are still partly mysterious. Some ceratopsian bone beds suggest that at least certain species gathered in groups, though whether these were permanent herds, seasonal gatherings, or animals brought together by drought or flood is still debated. Their display structures strongly suggest visual communication, and many species changed skull shape as they grew, meaning age may have affected status or behavior. Armored dinosaurs may have been more solitary in some cases, but they too had to find mates, recognize rivals, and navigate their environments. Their armor was not only a shield against death, it was part of a living body that grew, healed, aged, and interacted with others. By the end of the Cretaceous, horned and armored dinosaurs had become some of the most distinctive animals on Earth. They lived in a world rich with flowering plants, broad rivers, coastal plains, forests, and dangerous predators. They were not passive victims in that world. They were powerful herbivores with bodies shaped by millions of years of survival. When the asteroid struck at the end of the Cretaceous, these lineages vanished along with the other non-bird dinosaurs. Their armor, horns, frills, and tail clubs were no defense against a global catastrophe. But in the rocks they left behind, we can still read the story of their lives. The horned and armored dinosaurs show us that the dinosaur age was not only a story of giant predators and long-necked giants. It was also a story of shields, signals, weapons, and plant-eaters that became some of the most formidable creatures the land has ever known. Chapter 12. Duck-billed dinosaurs and herd life. Duck-billed dinosaurs, known scientifically as hadrosaurs, were among the great success stories of the late Cretaceous world. They were not the largest dinosaurs, not the most heavily armored, and not the most terrifying, yet they became some of the most widespread and abundant herbivores of their age. Their fossils have been found across North America, Asia, Europe, and other regions, often in large numbers, sometimes preserved in bone beds that suggest entire groups lived, moved, or died together. The name duck-billed dinosaur comes from the broad, flattened shape of the front of the mouth in many species, but this simple nickname can make them sound less remarkable than they truly were. Hadrosaurs were highly specialized plant-eaters with powerful jaws, complex teeth, strong bodies, and in many species, elaborate crests that may have helped them communicate. They were animals of floodplains, forests, coastal lowlands, river deltas, and seasonal landscapes. In many late Cretaceous ecosystems, they were not background creatures. They were central players, shaping vegetation, feeding predators, raising young, moving in groups, and leaving behind some of the richest evidence for dinosaur social life.
The success of hadrosaurs began with their feeding system. Earlier herbivorous dinosaurs had many ways of processing plants, but hadrosaurs developed one of the most sophisticated chewing mechanisms known among dinosaurs. Their mouths contained dental batteries, tightly packed columns of teeth that replaced themselves continuously as they wore down. Instead of relying on a few simple teeth, a hadrosaur had hundreds of teeth arranged into grinding and slicing surfaces. This allowed them to process tough vegetation efficiently, including leaves, twigs, conifers, horsetails, ferns, and later flowering plants. Their jaws were capable of complex movement, not exactly like mammalian chewing, but advanced enough to break down plant material far better than many earlier dinosaurs could. This mattered because digestion begins with processing. The more effectively an animal can break up food before swallowing, the more energy it can extract from the plants it eats. In a world where large herbivores had to consume great quantities of vegetation, such efficiency was a major advantage. Their broad beaks helped crop plants, while cheeks or cheek-like soft tissues may have helped keep food in the mouth during feeding. Behind the beak, the dental batteries did the heavy work. A herd of hadrosaurs feeding along a river valley would have been like a moving force of harvest, stripping vegetation, chewing constantly, and converting plant matter into muscle, bone, eggs, and movement. Hadrosaurs varied widely in size and shape, but many were large animals, often reaching 7 to 12 meters in length. They could move on all fours while feeding, but many were also capable of rising and walking or running on their hind legs when needed. Their bodies were deep and muscular, their tails long and stiffened for balance, and their limbs strong enough for long-distance movement. They were not helpless prey. A large hadrosaur could run, kick, shove, and use its size as protection. Still, they lived in a world of dangerous predators. In North America, hadrosaurs shared their habitats with tyrannosaurs such as Daspletosaurus, Gorgosaurus, Albertosaurus, and later Tyrannosaurus rex. In Asia, similar predator-prey relationships existed with Tarbosaurus and other large theropods. The abundance of hadrosaurs may have helped support these apex predators. A large meat-eating dinosaur needed large prey, and hadrosaurs were among the most important sources of food in many environments. But the relationship was not simple. Predators probably targeted the young, sick, old, isolated, or injured more often than healthy adults. A herd gave hadrosaurs protection through numbers, vigilance, and confusion. Many eyes could detect danger earlier. Many bodies could make it harder for a predator to isolate one target. Young animals may have been safer in groups than alone. Herd life, if present in many species, would have been one of the key reasons for hadrosaur success. Fossil evidence for herd behavior comes from several sources. Bone beds containing many individuals of the same species suggest that hadrosaurs sometimes gathered in large groups. Trackways show multiple dinosaurs moving in the same direction, sometimes with individuals of different sizes, which may indicate group movement across mudflats or river plains. Nesting sites provide even more intimate evidence. One of the most famous hadrosaurs, Maiasaura, whose name means good mother lizard, was found in association with nests, eggs, hatchlings, and juveniles. These discoveries suggested that at least some hadrosaurs nested in colonies and may have cared for their young after hatching. The babies were small and vulnerable, and evidence of worn teeth in some hatchlings has been interpreted as a sign that they remained in nests long enough to be fed or protected. The exact details are still debated, but the broader picture is powerful. Hadrosaurs were not simply laying eggs and walking away in every case. Some may have had complex reproductive behavior, nesting grounds, parental attention, and social structures that helped young survive. This makes them feel more like living animals and less like distant skeletons. Their crests add another fascinating dimension. Hadrosaurs are often divided into two major groups: Saurolophines, which generally lacked large hollow crests, and Lambeosaurines, many of which had elaborate skull crests. Parasaurolophus carried a long, backward-projecting, tube-like crest. Corythosaurus had a tall, rounded crest. Lambeosaurus had a hatchet-shaped crest. These structures were not random decorations. In many Lambeosaurines, the nasal passages ran through the crest, creating hollow chambers that may have affected sound production. Scientists have modeled these crests and suggested that they could produce deep, resonant calls, perhaps used for communication over distance, mating displays, species recognition, or group coordination. Imagine a Cretaceous floodplain at dusk, with herds moving among trees and low vegetation, and low, booming calls traveling through humid air. Such sounds would have made the hadrosaur world rich and alive. Crests may also have been visual signals. Their shapes differed between species, changed as individuals grew, and may have varied between sexes, though this is difficult to prove. Like the horns of ceratopsians or the feathers of theropods, hadrosaur crests show that dinosaurs lived in a world of communication and display. They had to recognize each other, attract mates, warn rivals, maintain contact, and perhaps signal danger. The Cretaceous was not silent. Hadrosaurs may have been among its great voices. Their herd life also raises questions about migration. Some hadrosaurs lived in high-latitude environments, including regions that experienced long seasonal darkness. Fossils from Arctic and near-polar areas show that dinosaurs were capable of living far beyond warm tropical habitats. Did hadrosaurs migrate seasonally, following food and light? Some may have. Others may have remained year-round, enduring cold and darkness in ways still being studied. Their strong limbs and group behavior would have made long-distance movement possible. Seasonal migration could help explain large herds and trackways, especially in environments where food availability changed across the year. Like modern caribou, wildebeest, or elephants, hadrosaurs may have moved through familiar routes, returning to nesting grounds, feeding grounds, or safer regions as conditions shifted. Even if not all species migrated, the possibility shows how dynamic their lives may have been. Hadrosaurs were also important because they lived during a time of botanical change. Flowering plants were spreading during the Cretaceous, and although older plants, such as conifers, ferns, and cycads, remained important, ecosystems were becoming more varied. Hadrosaurs, with their advanced feeding systems, may have been especially well-suited to exploit this changing plant world. Their success could be connected to their ability to eat many kinds of vegetation and process it efficiently. They were adaptable herbivores in a changing age. This adaptability helped them spread widely and become abundant in many regions. Their fossils are sometimes so common that they provide paleontologists with detailed information about growth, disease, injury, population structure, and variation. Some hadrosaur fossils preserve skin impressions, showing patterns of scales across the body. These impressions remind us that hadrosaurs were not smooth gray museum shapes, but textured animals with living skin, color patterns now mostly lost, muscles, scars, and individual differences. Some exceptional fossils even preserve body outlines, giving us rare glimpses of their real form beyond bone. In life, a hadrosaur herd would have been a remarkable sight. Adults moving heavily but steadily, juveniles staying near safer positions, crested individuals calling across open ground, beaks cropping plants, tails held stiff behind them, and the whole group alert to the possibility of predators.
Their world was full of danger, but also routine. Feeding, resting, nesting, moving, growing, calling, competing, and caring for young. They were successful because they combined efficient feeding, flexible movement, possible social organization, and reproductive strategies that allowed populations to thrive. When the asteroid struck at the end of the Cretaceous, hadrosaurs vanished with the other non-bird dinosaurs. Their herds, nesting grounds, calls, and feeding trails disappeared from the world. But their fossils preserve one of the clearest portraits of dinosaur community life. Through hadrosaurs, we see that dinosaurs were not merely isolated giants. They could be social, vocal, parental, migratory, and deeply connected to one another. Duck-billed dinosaurs show us the dinosaur age not as a collection of monsters, but as a living world of families, herds, landscapes, and ancient voices moving through the final chapters of the Mesozoic. Chapter 13. Feathers, Colors, and Display. For a long time, dinosaurs were imagined as huge, gray-green reptiles, heavy, scaly, silent, and almost entirely without decoration. In older paintings and films, they often looked like oversized lizards, their bodies covered in dull skin, their movements slow, and their world strangely colorless. Modern paleontology has changed that picture dramatically. Dinosaurs were far more visually diverse than people once believed. Many still had scales, especially large-bodied herbivores and some big predators, but others carried feathers, filaments, bristles, crests, horns, plates, frills, and display structures that made them living signals as much as living machines. The discovery of feathered dinosaurs, especially from exceptionally preserved fossils in China and other regions, transformed our understanding of what dinosaurs looked like and how they lived. Feathers were not an invention that appeared suddenly with birds. They evolved within theropod dinosaurs and probably began as simple filament-like structures long before true powered flight. These early feathers may have looked more like fuzz or hair-like coverings than the complex flight feathers of modern birds. Their first functions were likely not flight, but insulation, display, sensory roles, or a combination of these. Small animals lose heat more quickly than large ones, so a covering of simple feathers could help a small dinosaur maintain body temperature, especially in cooler climates or at night. Over time, these simple structures became more complex. Some branched, some formed veins, some became symmetrical feathers useful for display or insulation, while others eventually became asymmetrical flight feathers suited for aerodynamic control. The path from simple filaments to wings was not a straight road built for flight from the beginning. Evolution often works by modifying existing structures for new purposes, and feathers are one of the clearest examples. A feature that may have first helped a small dinosaur stay warm could later help another glide, maneuver, brood eggs, attract mates, or fly. Feathered dinosaurs included many small theropods close to the ancestry of birds, but feathers were not limited to animals that could fly. Velociraptor, for example, almost certainly had feathers, even though it was not a flying animal. Evidence from related fossils and quill knobs on the bones of some dromaeosaurs suggests that their arms supported feathers. These feathers may have been used for display, balance, covering eggs, or communication. Oviraptorosaurs, troodontids, dromaeosaurs, and early birds all reveal a world in which feathers were widespread among bird-like theropods. Some larger tyrannosauroid relatives also show evidence of feather-like coverings, especially earlier or smaller forms. This does not mean every dinosaur was fully feathered. Large animals often face different temperature pressures, and many preserved skin impressions from big dinosaurs show scales. Tyrannosaurus rex, for instance, may have had scaly regions, though the full extent of any feathering remains debated. The important point is that dinosaurs were not one thing. Some were scaly, some were feathered, some may have had a mixture of both,
and their appearance likely changed with age, species, climate, and body region. Young animals may have been fluffier than adults. Dinosaurs living in cooler regions may have benefited from more insulation. Display feathers could appear on arms, tails, heads, or bodies without covering the entire animal. The dinosaur world was visually complex. Color is harder to study than feathers because color rarely fossilizes in an obvious way.
Yet, in some exceptional fossils, scientists have found microscopic structures called melanosomes, which are associated with pigments in modern feathers. By comparing fossil melanosomes with those in living birds, researchers can sometimes infer possible colors or patterns. This has allowed paleontologists to reconstruct aspects of color in a few feathered dinosaurs and early birds. Some may have had reddish-brown tones, dark stripes, pale patches, glossy black feathers, or contrasting patterns. Anchiornis, a small feathered dinosaur from the Jurassic of China, has been reconstructed with striking black, white, and reddish markings. Sinosauropteryx appears to have had a banded tail and reddish coloration. These discoveries are astonishing because they do not merely tell us that dinosaurs had feathers. They suggest that some dinosaurs had patterns, contrast, and visual identities. They were not blank creatures. They could be striped, speckled, shaded, bright, dark, or patterned in ways that affected survival and behavior. Color could serve many purposes. Camouflage is one of the most obvious. A small dinosaur living among shadows, branches, leaves, or dry ground could avoid predators or approach prey more effectively with body patterns that broke up its outline. Countershading, where the upper body is darker and the underside lighter, is common in many modern animals and may have existed in some dinosaurs. But color is not only for hiding, it is also for being seen. Modern birds use color for courtship, territorial display, warning, species recognition, and social communication. Since birds are living dinosaurs, it is reasonable to imagine that many non-bird dinosaurs also used visual signals in complex ways. A crest, feather fan, bright patch of skin, patterned tail, or colored frill could help an animal attract mates, intimidate rivals, signal maturity, or recognize members of its own species. Display may have been especially important because many dinosaur groups evolved extravagant structures that seemed too elaborate to be explained by defense or feeding alone. Ceratopsian frills, hadrosaur crests, theropod feathers, stegosaur plates, pachycephalosaur domes, and various horns and ridges all suggest that dinosaurs lived in a world of visual communication. The plates of Stegosaurus, for example, may have helped with display as much as defense or temperature regulation. They were large, distinctive, and arranged in a way that would have made the animal highly recognizable. If covered with blood-rich tissue or colored skin, they could have been far more striking in life than fossil bone suggests. Ceratopsian frills may have carried colors or patterns used in species recognition and mating displays. Hadrosaur crests may have combined visual display with sound production, turning the head into both a sign and an instrument. Theropod feathers could have been raised, spread, shaken, or arranged during courtship or threat displays. A feathered dinosaur spreading its arms or tail may have looked less like a reptile and more like a strange prehistoric bird of paradise. This does not mean dinosaurs behaved exactly like modern birds, but it does mean the comparison is useful. Birds show how feathers, color, posture, sound, and movement can become part of elaborate social behavior. Dinosaurs may have danced, bowed, inflated throat tissues, flashed colors, clashed horns, displayed tails, called across valleys, or guarded territories with ritualized gestures. Much of this behavior leaves only indirect fossil evidence, but anatomy can reveal possibility. Structures that are highly visible, species-specific, and costly to grow often suggest display. In evolution, display matters because reproduction matters. An animal that looks stronger, healthier, more mature, or more attractive may gain better access to mates. Over generations, sexual selection can produce astonishing forms, from peacock tails to deer antlers. Dinosaurs almost certainly experienced similar pressures. Feathers also changed the way dinosaurs cared for their young. In modern birds, feathers help cover eggs and chicks, preserving warmth and protection. Fossils of oviraptorosaurs preserved sitting over nests suggest brooding behavior, with arms arranged around eggs in a way that resembles bird nesting posture. Feathers on the arms could have helped shield eggs from temperature changes, sunlight, or rain. This is one of the most intimate images in paleontology, a feathered dinosaur crouched over a nest, not as a monster, but as a parent guarding the next generation. Feathers may also have helped young dinosaurs survive after hatching, keeping them warm during vulnerable stages of growth. In some species, juveniles may have looked very different from adults, with different proportions, coverings, or colors. This kind of change is common in living animals. A young dinosaur might need camouflage, while an adult might need display. A hatchling might need insulation, while a massive adult might need to shed heat more effectively. The study of dinosaur appearance is still developing, and many questions remain uncertain. We do not know the colors of most dinosaurs. We do not know exactly how much feathering covered many species. We do not know the full range of soft tissues, skin flaps, wattles, keratin coverings, or seasonal changes they may have had. Fossils preserve bones more often than skin, and skin more often than color or behavior. But even with these limits, the old image of dinosaurs as dull, oversized reptiles can no longer survive. They were varied, textured, and often spectacular. Some had pebbly scales, some had armor, some had horns covered in keratin, some had feathers along their arms and tails, some had crests that may have resonated with sound, some had patterns that helped them hide, and others may have carried colors meant to be noticed from far away. Their world was not silent and gray. It was filled with movement, calls, postures, mating displays, defensive signals, warning colors, camouflage patterns, and social recognition. The discovery of feathers has also changed the emotional meaning of dinosaurs. It brings them closer to the living world. When we look at a crow, an eagle, an ostrich, or a sparrow, we are not seeing something merely similar to dinosaurs. We are seeing the surviving branch of the dinosaur family tree. The feathers of modern birds are part of a story that began deep in the Mesozoic, among small theropods that could not have known they were carrying the future. The colors of birds, their displays, their songs, their nests, and their movements all echo ancient possibilities. Non-bird dinosaurs are gone, but their legacy is not only bones in museums. It is also the shimmer of feathers, the tilt of a bird's head, the spread of a wing, and the bright language of display that still fills the modern world. Feathers, colors, and display reveal dinosaurs not as crude monsters, but as living animals with bodies meant to communicate, survive, and reproduce. They make the dinosaur age richer, stranger, and more beautiful than the old pictures ever allowed. Chapter 14. Dinosaur Behavior. Dinosaur behavior is one of the most fascinating and difficult parts of paleontology, because behavior rarely fossilizes directly. Bones can tell us the size of an animal, the shape of its skull, the strength of its limbs, or the structure of its teeth, but they do not easily preserve a moment of fear, courtship, play, migration, parental care, or communication. Yet dinosaurs were not statues made of bone. They were living animals, and every living animal behaves. They searched for food, avoided danger, competed with rivals, found mates, nested, grew, rested, moved through landscapes, responded to seasons, and interacted with members of their own species.
To understand dinosaurs properly, we must move beyond the old image of solitary monsters wandering through empty prehistoric scenery. The dinosaur world was full of action, routine, instinct, learning, signals, and relationships.
Paleontologists reconstruct these behaviors using many kinds of evidence: fossilized footprints, nests, eggs, bone beds, injuries, growth patterns, tooth marks, comparisons with living birds and crocodilians, and the structure of dinosaur bodies themselves. This evidence does not reveal everything, and scientists must be careful not to invent details without support. But it does allow us to glimpse the lives behind the skeletons. One of the clearest areas of dinosaur behavior is nesting. Dinosaurs laid eggs, as birds and crocodilians do today, and fossilized eggs have been found in many parts of the world. Some are isolated, while others occur in nesting colonies, suggesting that certain dinosaurs returned to particular places to reproduce or gathered in groups during the breeding season. Hadrosaurs, such as Maiasaura, are especially famous for nesting evidence. Fossils associated with nests, eggs, hatchlings, and juveniles suggest that these dinosaurs may have cared for their young, at least for some period after hatching. The name Maiasaura means good mother lizard, and although scientists must be cautious with emotional language, the evidence points toward a more complex reproductive life than simply laying eggs and abandoning them immediately. Some hatchlings appear to have remained in or near nests long enough to grow, which may mean adults protected or fed them. Oviraptorosaurs provide another intimate image of dinosaur behavior. Some fossils preserve adults positioned over nests, with their limbs arranged around eggs in a posture similar to brooding birds. This does not prove that every dinosaur brooded eggs in the same way, but it strongly suggests that at least some feathered theropods used their bodies, and perhaps their feathered arms, to cover and protect their eggs. Such fossils are powerful because they capture not just anatomy, but an act, an animal over its nest, frozen by death and preserved for millions of years. Social behavior is another important theme. Some dinosaurs appear to have lived or moved in groups, at least at certain times. Trackways sometimes show multiple individuals traveling in the same direction, and bone beds may contain many members of one species. Hadrosaurs, ceratopsians, sauropods, and some theropods have all been discussed in connection with group behavior. Herd life could provide many advantages. It could help animals detect predators earlier, protect young, find food, migrate, and coordinate movement across dangerous landscapes. A herd of hadrosaurs moving through a late Cretaceous floodplain would have been a complex living community, with adults, juveniles, calls, alarm signals, feeding behavior, and constant awareness of danger. Ceratopsian bone beds suggest that some horned dinosaurs may also have gathered in groups, though whether these were permanent herds, temporary seasonal gatherings, or animals brought together by drought, flood, or disaster is still debated. Sauropod trackways sometimes show several animals moving together, and in some cases, smaller individuals appear separated from larger ones, which may hint at age-based grouping or different movement patterns. Even if not all dinosaurs were social all the time, it is clear that many were not purely solitary. Their lives included repeated contact with others of their kind. Communication must have been essential. Dinosaurs likely communicated through sound, posture, movement, color, touch, and visual display. Hadrosaurs with hollow crests, such as Parasaurolophus and Corythosaurus, may have produced low resonant calls, allowing individuals to signal across forests or open plains. Ceratopsians used horns and frills that may have carried visual meaning: species recognition, maturity, strength, mating status, or threat display. Theropods with feathers may have raised or spread them during courtship or aggression, much as birds use wings, tails, and plumage today. Stegosaur plates, pachycephalosaur domes, theropod crests, and many other structures may have played roles in display.
Sound is harder to reconstruct because soft vocal organs rarely fossilize, but dinosaurs almost certainly were not silent. Their world may have included deep calls, hisses, booming sounds, foot stomps, wing or feather movements, and other signals unlike anything we can exactly reproduce. Since birds are living dinosaurs and crocodilians are their closest living relatives outside birds, both groups provide useful clues. Crocodilians use deep bellows, body vibrations, jaw slaps, and parental calls. Birds use songs, cries, dances, feather displays, and complex social signals. Non-bird dinosaurs may have occupied a broad range between these living relatives, with their own extinct forms of communication. Fighting and competition were also part of dinosaur behavior. Many animals compete for mates, territory, food, nesting sites, or social rank, and dinosaurs likely did the same. Fossil injuries can reveal moments of conflict. Bite marks on bones show predator attacks or scavenging, but some wounds may also indicate fights between members of the same species. Tyrannosaur skulls sometimes show healed bite marks that appear to have been made by other tyrannosaurs, suggesting face-biting behavior during conflict. Ceratopsian horns and frills may have been used in contests, perhaps with individuals locking horns, pushing, or displaying before physical combat. Pachycephalosaurs, with their thick skull domes, have long been imagined as head-butting animals, though exactly how they used those skulls remains debated. They may have butted heads, struck flanks, or used their domes mostly for display. Whatever the details, competition would have shaped behavior strongly. A dinosaur did not only have to survive predators, it also had to deal with rivals of its own kind. Feeding behavior varied enormously across dinosaur groups. Sauropods likely spent much of their time consuming huge amounts of vegetation, using long necks to sweep across feeding zones while their large digestive systems processed tough plant matter. Hadrosaurs cropped and chewed plants with advanced dental batteries. Ceratopsians used strong beaks and slicing teeth to process vegetation. Ankylosaurs fed low to the ground, protected by armor as they moved slowly through their habitats. Predatory dinosaurs behaved differently depending on size, anatomy, prey, and environment. A large theropod, such as Allosaurus or Tyrannosaurus, may have hunted vulnerable animals, scavenged carcasses, defended feeding sites, or followed herds. Smaller theropods may have hunted insects, mammals, lizards, juvenile dinosaurs, eggs, or small birds, and pterosaurs. Predators had to balance hunger with risk. A failed hunt could waste energy. An injury could be fatal. For that reason, dinosaur predators probably behaved with more caution than films suggest. They were not constantly charging into battle. They watched, waited, smelled, listened, followed, and chose opportunities. Migration may also have shaped dinosaur lives. Some dinosaurs lived in seasonal environments, including high-latitude regions where winter darkness could last for long periods. Fossils from polar regions show that dinosaurs could survive in places far from the warm, tropical image often associated with them. Some may have migrated seasonally to follow food, nesting conditions, or better climates. Others may have stayed year-round, adapting to cold, darkness, and seasonal scarcity. Large herbivores are especially likely candidates for long-distance movement because they require enormous amounts of food and can transform local vegetation quickly. Trackways preserve moments of movement across mud, sand, or riverbanks, sometimes showing direction, speed, and group arrangement. These footprints are among the most direct records of dinosaur behavior. A footprint is not just a trace of anatomy, it is a preserved step. It shows that an animal passed through a place at a particular moment, perhaps walking calmly, running, limping, traveling with others, or crossing a shoreline. Resting traces, tail marks, nest scrapes, and feeding traces can also reveal how dinosaurs used their bodies and environments. Growth behavior is another key part of their story. Dinosaurs changed as they aged. Juveniles were often not simply small adults. Young tyrannosaurs were more slender and agile than mature adults, possibly hunting different prey.
Young ceratopsians had smaller horns and frills that changed dramatically with age. Young sauropods were tiny compared with adults and may have lived differently until they grew large enough to be safer from predators. These changes mean dinosaur behavior may have shifted across a lifetime. A hatchling, juvenile, subadult, and adult could occupy different ecological roles. Some species may have formed age-based groups, others may have protected young, while some young animals may have survived independently from the beginning. The variety was likely enormous. Ultimately, dinosaur behavior reminds us that these animals were not symbols first. They were organisms. They had daily lives. They woke, rested, fed, searched, hid, displayed, nested, fought, fled, and sometimes cared for their young. They responded to weather, seasons, injury, hunger, fear, and opportunity. Much of this is lost forever because behavior is fragile and time is immense. But enough evidence remains to bring the dinosaur world back into motion. Nests show reproduction. Trackways show journeys. Injuries show conflict and survival. Bone beds hint at groups. Crests and feathers suggest communication. Teeth and jaws reveal feeding. Living birds carry part of the behavioral legacy of theropod dinosaurs into the present. When a bird builds a nest, guards its eggs, calls to others, displays feathers, or moves with quick, alert intelligence, we are seeing echoes of ancient dinosaur behavior. The non-bird dinosaurs are gone, but they were never lifeless monsters. They were active, responsive, social, competitive, and sometimes caring animals, living complicated lives across more than 160 million years of Earth's history. Chapter 15. Dinosaur Senses and Intelligence. Dinosaurs lived in a world that demanded attention. Every animal, whether hunter or plant-eater, had to read its surroundings constantly. A shadow moving behind trees, the scent of a carcass on the wind, the vibration of footsteps through the ground, the shape of a rival's crest, the call of a herd member, the movement of insects in leaf litter, the glimmer of water in a dry season, with the sudden silence of smaller animals, could all matter. To survive, dinosaurs needed senses suited to their lives, and those senses varied enormously from one group to another. There was no single dinosaur mind, just as there is no single mammal mind today. A sauropod, a tyrannosaur, a hadrosaur, a dromaeosaur, and an ankylosaur experienced the world differently because their bodies, diets, dangers, and behaviors were different. Paleontologists study dinosaur senses and intelligence through skulls, brain cases, eye sockets, inner ears, nasal cavities, comparisons with living birds and crocodilians, and rare clues from behavior preserved in fossils. The picture that emerges is not of slow, stupid reptiles, but of animals with specialized abilities, some simple, some surprisingly advanced, all shaped by the demands of ancient life. Vision was one of the most important senses for many dinosaurs. Predatory theropods often had forward-facing eyes to some degree, giving them binocular vision, which helps an animal judge distance and depth. This would have been valuable for hunters that needed to strike accurately, chase moving prey, or navigate complex terrain. Tyrannosaurus rex, for example, had eyes positioned in a way that likely gave it strong depth perception compared with many other dinosaurs. It needed to judge the distance to a triceratops, a hadrosaur, or a carcass contested by rivals. Smaller predatory dinosaurs may also have relied heavily on vision, especially those that hunted quick prey such as lizards, early mammals, insects, or small dinosaurs. In some bird-like theropods, large eye sockets suggest keen eyesight, perhaps useful in low light. Troodontids, for instance, had relatively large eyes and brains for their body size, and some scientists have suggested that they may have been active in dim conditions, though exact habits remain debated. Herbivorous dinosaurs also depended on vision, but often in a different way.
Many plant eaters had eyes placed more to the sides of the head, giving them a wider field of view. This is common in prey animals today. A wide field of vision helps detect approaching danger from many directions. A hadrosaur feeding in a herd, a ceratopsian browsing near a forest edge, or a small ornithischian moving through low vegetation would benefit from spotting predators early. For them, survival often began with awareness. Smell was another powerful sense, especially in large theropods. The skulls of tyrannosaurs show large olfactory regions, suggesting that they had an excellent sense of smell. This could help them detect carcasses from far away, locate prey, recognize territories, identify other individuals, or track environmental signals. A strong sense of smell does not mean an animal was only a scavenger. Modern predators that hunt actively, such as wolves, bears, and some birds, can also have excellent smell. For Tyrannosaurus rex, smell would have been useful in almost every part of life. It could follow the scent of a wounded animal, detect a dead dinosaur hidden by vegetation, recognize the presence of another tyrannosaur, or investigate nesting grounds and travel routes. Other theropods may have had different sensory balances. Some probably relied more on vision, others on smell, depending on skull structure and lifestyle. Herbivores also used smell, though it may have served different needs: finding food, recognizing mates, detecting predators, identifying offspring, or sensing water and environmental changes. The ancient world was full of odors: plants, mud, decay, blood, rain, volcanic ash, nests, dung, and the bodies of other animals. Dinosaurs moved through this invisible chemical landscape as much as through a visible one. Hearing is harder to reconstruct, but the inner ear gives important clues. The inner ear helps with both hearing and balance, and its shape can reveal something about the frequencies an animal may have detected and how it moved its head. Many dinosaurs probably heard low-frequency sounds well. This would be especially useful for large animals communicating over long distances. Hadrosaurs with hollow crests may have produced deep, resonant calls, and those calls would require listeners capable of detecting them. A herd spread across a floodplain or forested valley could use sound to maintain contact, warn of danger, attract mates, or coordinate movement. Ceratopsians, sauropods, and other large dinosaurs may also have used low-frequency sounds, though the exact nature of their vocalizations remains uncertain. Dinosaur hearing was not necessarily like birdsong or mammal speech. It may have included booms, bellows, rumbles, hisses, calls, and body-generated sounds. The world of dinosaurs was likely much noisier and more communicative than older, silent depictions suggest. Balance and spatial awareness were especially important for bipedal dinosaurs. Theropods walked and ran on two legs, using long tails and body posture to maintain stability. Their inner ears and brain regions connected to balance had to support quick movements, turning, lunging, and head control. A predator chasing prey or striking with its jaws needed coordination. A small, feathered theropod, leaping, climbing, or flapping its feathered arms, needed even more precise control. In the lineage leading toward birds, balance, vision, and motor coordination became increasingly refined. Flight did not emerge from clumsy animals. It emerged from agile theropods already capable of complex movement. Even non-flying feathered dinosaurs may have used their limbs and tails for balance, display, braking, or maneuvering through uneven habitats. Intelligence in dinosaurs must be discussed carefully. It is tempting to rank animals as smart or stupid, but intelligence is not one simple ladder. It is a set of abilities shaped by lifestyle. A predator may need problem-solving, memory, sensory integration, and hunting judgment. A social herbivore may need recognition of group members, migration routes, alarm responses, and nesting behavior. A small nocturnal animal may need excellent spatial memory and caution.
A giant sauropod may not need the same kind of quick predatory intelligence, but it still needed to find food, move through landscapes, reproduce, and respond to danger. Brain size relative to body size can provide some clues, but it is not a perfect measure. Many large dinosaurs had small brains compared with their huge bodies, but that does not mean they were barely functional. Their brains controlled enormous bodies and behaviors appropriate to their ecological roles. Sauropods did not need to solve puzzles like crows. They needed to manage movement, feeding, social contact, and survival at gigantic scale. Theropods, especially smaller bird-like forms, often had relatively larger brains. Troodontids and dromaeosaurs are frequently discussed as among the more intelligent non-bird dinosaurs, with brain proportions closer to those of some modern birds than to many reptiles. This does not mean they were human-like thinkers, but they may have been alert, flexible, and behaviorally complex. Birds, the living descendants of theropod dinosaurs, show that dinosaur line brains were capable of remarkable sophistication. Modern crows, parrots, ravens, and some other birds solve problems, use tools, recognize individuals, remember locations, and display complex social behavior. We should not project all modern bird intelligence backward onto every dinosaur, but birds prove that the dinosaur lineage had enormous neurological potential. The roots of that potential reach into the Mesozoic, especially among small, active, feathered theropods. Some dinosaurs may have had strong memory for places. Migratory species would need to remember routes, seasonal feeding grounds, nesting areas, and water sources. Herding animals would need to respond to social signals and predator threats. Nesting dinosaurs may have recognized nesting sites or offspring, at least in some species. Predators may have learned from experience, avoiding dangerous prey or returning to places where carcasses were likely. Even reptiles today can show more learning and behavioral flexibility than once assumed, and birds are among the most intelligent animals alive. Dinosaurs, positioned evolutionarily between these living relatives, likely showed a broad spectrum of mental abilities. Their intelligence was not human intelligence, but it was real animal intelligence, practical, sensory, embodied, and shaped by survival. The senses of dinosaurs also influenced their appearance and display. A colorful frill, feather fan, crest, horn, or body posture only matters if other animals can perceive it. The evolution of display structures suggests that many dinosaurs were visually attentive to shape, size, movement, and perhaps color. The crests of hadrosaurs suggest hearing and sound production mattered. The face-biting evidence in Tyrannosaurs suggests individuals recognized and interacted with rivals at close range. Nesting behavior suggests responses to eggs and young. Trackways showing group movement suggest awareness of others. Intelligence is not only found in the skull, it is expressed in behavior across the whole body and social world. To imagine dinosaur senses is to make the Mesozoic alive again. A tyrannosaur lifts its head to scent the air after rain. A herd of hadrosaurs hears a distant low call and shifts direction. A small feathered theropod watches insects moving across bark. A ceratopsian sees the posture of a rival and lowers its horned head. A sauropod feels the movement of the herd around it as it feeds across a floodplain. An oviraptorosaur settles over a nest, responding to eggs beneath its body. None of these animals understood the world as humans do, but they did not need to. They had their own worlds of sight, smell, sound, balance, memory, instinct, and learned experience. Dinosaur intelligence was not a single mystery to be solved with one number. It was a living spectrum across thousands of species and more than 160 million years. Some dinosaurs were simple in certain ways, others highly alert and complex. Some depended on smell, others on vision, others on sound, movement, or group awareness. Together, their senses made the dinosaur age more than a world of bodies. It was a world of perception, where every creature lived inside its own ancient experience of danger, food, weather, rivals, mates, offspring, and survival. Chapter 16. The Oceans and Skies of the Dinosaur Age. The age of dinosaurs was not ruled by dinosaurs alone. Although dinosaurs dominated many land ecosystems for more than 160 million years, the world around them was filled with other extraordinary reptiles, birds, mammals, fish, insects, and marine creatures. Some of the most spectacular animals of the Mesozoic era were not dinosaurs at all, even though they are often placed beside dinosaurs in popular imagination. The great marine reptiles were not dinosaurs. The flying pterosaurs were not dinosaurs. Even the enormous sea predators and winged giants that lived at the same time belonged to different branches of reptile evolution. This distinction matters because it shows how rich the Mesozoic world truly was. Dinosaurs were the central land animals, but the oceans and skies followed their own evolutionary stories, filled with hunters, gliders, swimmers, divers, and strange experiments in body design. To understand the full dinosaur age, we must look beyond the forests and floodplains and enter the warm seas and wide skies that surrounded them. The oceans of the Mesozoic were vast, dynamic, and full of life. As Pangaea broke apart, new coastlines appeared, shallow seas flooded continental interiors, and marine ecosystems became increasingly complex. In the Triassic, after the terrible Permian extinction, ocean life was still recovering. But over time, new marine reptiles evolved to fill predatory roles once left empty. Among the earliest and most successful were the ichthyosaurs. These animals are often compared to dolphins because many developed streamlined bodies, long snouts, large eyes, and powerful tails suited for fast swimming. But they were reptiles, not mammals, and their dolphin-like shape is an example of convergent evolution, when unrelated animals evolve similar bodies because they face similar challenges. A fast marine hunter needs a body that cuts through water efficiently, whether it is an ichthyosaur, a dolphin, a tuna, or a shark. Some ichthyosaurs were modest in size, while others became enormous. They hunted fish, squid-like cephalopods, and other marine animals, moving through Mesozoic seas with speed and precision. Their large eyes suggest that some may have hunted in deep or dim water, where light was limited. Unlike many reptiles, ichthyosaurs gave birth to live young rather than laying eggs on land, an adaptation essential for animals fully committed to life in the sea. Fossils of pregnant ichthyosaurs preserve this intimate detail, showing that their lives, births, and deaths all took place in the ocean. Plesiosaurs followed a very different design. Instead of the sleek, dolphin-like form of ichthyosaurs, plesiosaurs had broad bodies, 4 powerful flippers, and, in many species, extremely long necks. Their body plan seems strange because no modern animal looks exactly like them. Some plesiosaurs, especially the long-necked forms, may have used their necks to strike at fish or small prey, moving their heads with precision while the body remained more stable. Others, known as pliosaurs, had shorter necks, enormous heads, and powerful jaws. Pliosaurs were among the apex predators of Jurassic and Cretaceous seas. Animals such as Leopleurodon and Kronosaurus were built for strength, with massive skulls and teeth capable of gripping large prey. They could attack fish, marine reptiles, and almost anything they could overpower. The contrast between long-necked plesiosaurs and short-necked pliosaurs shows how one larger group could explore very different predatory strategies. One became elegant and almost swan-like in silhouette, though still dangerous. The other became a massive-headed ocean hunter, closer in ecological role to a killer whale or great white shark. Later in the Cretaceous, another group rose to prominence: the mosasaurs. Mosasaurs were marine lizards related to monitor lizards and snakes, and they became some of the dominant ocean predators near the end of the dinosaur age. They had long bodies, powerful tails, paddle-like limbs, and jaws filled with sharp teeth. Some were relatively small and may have hunted fish in coastal waters. Others became gigantic apex predators, capable of attacking large prey, including fish, turtles, ammonites, birds, and other marine reptiles. Mosasaurs appeared after ichthyosaurs had declined and eventually vanished, and they became especially important in the late Cretaceous seas. Their rise shows that the ocean world, like the land, changed across time. There was no single permanent ruler. Different groups rose, diversified, and disappeared as climates shifted, seas opened and closed, prey changed, and extinction events altered ecosystems. Alongside these marine reptiles lived sharks, rays, bony fish, ammonites, belemnites, sea turtles, crustaceans, plankton, corals, and many other organisms. Ammonites, with their coiled shells, were especially abundant and diverse, filling the seas in countless forms. They were prey for many animals and important markers for paleontologists because their fossils help date rock layers. The oceans were not empty backgrounds beneath the dinosaur world. They were entire civilizations of life, with food webs as complex as those on land. Shallow seas could be especially productive, filled with fish, invertebrates, reefs, and predators. In places like the western interior seaway of North America, a vast inland sea split the continent during parts of the Cretaceous, creating marine environments where mosasaurs, plesiosaurs, giant fish, sea turtles, and flying pterosaurs lived near the same regions where dinosaurs roamed on land. A dinosaur might have walked along a coastal plain while, not far away, a mosasaur hunted below the waves, and pterosaurs crossed the sky above. The skies of the Mesozoic belonged first not to birds, but to pterosaurs. Pterosaurs were the first vertebrates to achieve powered flight, appearing in the late Triassic and surviving until the end of the Cretaceous. They were close relatives of dinosaurs within the broader Archosaur group, but they were not dinosaurs themselves. Their wings were unlike the wings of birds or bats. A pterosaur wing was supported mainly by an enormously elongated fourth finger, with a membrane stretching from that finger along the body and sometimes to the legs. This design allowed them to fly in many different ways. Some early pterosaurs were small, with long tails and sharp teeth, likely hunting insects, fish, or small vertebrates. Over time, pterosaurs diversified into many forms, from agile forest flyers to ocean-going soarers with long, narrow wings. Some had elaborate crests on their heads, which may have served for display, species recognition, or sexual selection. Like dinosaurs, pterosaurs were not dull reptiles. Many may have been covered in hair-like filaments called pycnofibers, which probably helped with insulation and may have given them a fuzzy appearance. Their bodies were light, their bones often hollow, and their flight abilities highly refined. One of the most remarkable things about pterosaurs is the range of sizes they achieved. Some were no larger than small birds, while others became the largest flying animals ever known. In the late Cretaceous, Ashdarchid pterosaurs such as Quetzalcoatlus and Hatzegopteryx reached wingspans comparable to small aircraft. These giants were not simply oversized seagulls. Their long necks, long limbs, and strong bodies suggest that some may have spent much of their time walking on land, stalking small animals like enormous winged storks. Others soared over coastlines and oceans. The exact lifestyles of the largest pterosaurs remain debated, but their existence shows how extreme vertebrate flight became during the Mesozoic. Imagine a Cretaceous plain where herds of dinosaurs move below while a giraffe-sized pterosaur walks across the ground, folding its enormous wings and searching for prey. Such a scene would feel almost mythical, yet it belonged to the real history of Earth. Birds entered the skies later, evolving from small, feathered theropod dinosaurs during the Jurassic. At first, early birds shared the air with pterosaurs rather than replacing them. Archaeopteryx from the late Jurassic shows a mixture of bird-like and dinosaur-like features, feathers and wings, but also teeth, claws, and a long, bony tail. During the Cretaceous, birds diversified into many forms. Some retained teeth, some lived near water, some flew strongly, while others had different degrees of flight ability. Birds and pterosaurs likely occupied different niches, at least for much of their shared history. Pterosaurs included many large, soaring, and specialized forms, while birds gradually became more varied among smaller aerial and ecological roles. The sky was therefore not a simple kingdom with one ruler. It was layered: insects, pterosaurs, early birds, gliding animals, and perhaps small feathered dinosaurs using wings or wing-like limbs for display, balance, or short aerial movements. Insects were also transforming during the Dinosaur Age, especially as flowering plants spread in the Cretaceous. Pollinating insects, beetles, flies, wasps, and other groups interacted with plants and helped shape ecosystems from below. The air was alive at many scales, from tiny insects to vast pterosaurs. The relationship between land, sea, and sky made the Mesozoic world deeply interconnected. Coastal environments brought these realms together. A dead marine reptile washed ashore could feed land scavengers. A pterosaur could nest inland but feed at sea. A bird could hunt insects along a river near dinosaur nesting grounds. Rivers carried nutrients from dinosaur landscapes into seas. Storms, floods, tides, and seasonal changes connected habitats that might seem separate. Even extinction events crossed boundaries. When the asteroid struck at the end of the Cretaceous, it did not only affect land dinosaurs. It disrupted oceans, skies, forests, plankton, food chains, and climate systems. Pterosaurs vanished, mosasaurs vanished, plesiosaurs vanished, ammonites vanished. Many birds died out, though one branch survived and later gave rise to the birds of the modern world. The end of the Dinosaur Age was also the end of many oceanic and aerial dynasties. But before that ending, the Mesozoic was one of the most spectacular periods of life in 3 dimensions. On land, dinosaurs browsed, hunted, nested, and migrated. In the oceans, ichthyosaurs, plesiosaurs, pliosaurs, and mosasaurs pursued prey through warm seas. In the skies, pterosaurs soared, early birds fluttered and flew, and insects moved among ancient plants. These worlds were different, but they belonged to the same planet and the same grand story. The oceans and skies of the Dinosaur Age remind us that the Mesozoic was not merely an age of dinosaurs. It was an age of extraordinary reptiles, ancient birds, strange seas, giant flyers, and ecosystems that stretched from the ocean depths to the highest air. Dinosaurs were the most famous inhabitants of that age, but they were surrounded by an even larger world, restless, alive, and filled with forms of life as strange and magnificent as the giants on land. Chapter 17. The Origin of Birds. The origin of birds is one of the most remarkable stories in the history of evolution, because it reveals that dinosaurs did not completely disappear from the Earth. One branch survived, transformed, and still lives around us today. Birds are not merely related to dinosaurs in a distant or poetic sense. They are living dinosaurs, descendants of small feathered theropods that evolved during the Mesozoic era. This idea, once debated fiercely, is now one of the central conclusions of modern paleontology. The connection between birds and dinosaurs can be seen in bones, feathers, eggs, nests, breathing systems, growth patterns, and behavior.
It is a story that begins not with a sudden leap into the sky, but with small changes accumulating over millions of years. Lighter skeletons, longer arms, feathers, improved balance, sharper vision, complex movement, and new ways of using the body. Long before the first true birds appeared, their dinosaur ancestors were already experimenting with features that would later make flight possible. These ancestors belonged to the theropods, the same broad group that included giant predators such as Allosaurus and Tyrannosaurus, but the bird line came from much smaller and more agile forms. Small theropods were often active animals with long hind limbs, balancing tails, grasping hands, and sharp senses. Many had feathers or feather-like coverings, not originally for flight, but probably for insulation, display, brooding eggs, camouflage, and communication. This is one of the most important points in the origin of birds. Feathers did not begin as flight equipment. They were useful before flight existed. Simple filaments could help an animal stay warm. More complex feathers could create visual displays, cover nests, protect young, or help with balance. Only later did some feathers become shaped in ways that allowed gliding, steering, and powered flight. Evolution often works this way. A structure evolves for one function, then becomes useful for another. The wing of a bird did not appear fully formed in one generation. It developed from the forelimbs of feathered dinosaurs, whose arms were already being used in varied ways. The famous fossil Archaeopteryx from the late Jurassic has long stood as a symbol of this transition. It had feathers and wings, and it was capable of some form of flight or gliding. But it also had many clearly dinosaurian traits: teeth in its jaws, clawed fingers, a long bony tail, and a body that still looked much like a small theropod. Archaeopteryx was not a modern bird, but it was not simply a reptile with feathers either. It occupied a fascinating middle ground, showing that the boundary between non-bird dinosaurs and birds was gradual. Since its discovery, many more fossils have deepened this picture. Feathered dinosaurs from China and other regions have shown that many traits once considered uniquely bird-like were already present in non-bird theropods. Animals such as Anchiornis, Microraptor, Caudipteryx, Sinosauropteryx, and many dromaeosaurs and troodontids reveal a world of feathered dinosaurs with different body plans, feather arrangements, and possible behaviors. Microraptor, for example, had long feathers not only on its arms, but also on its legs, giving it a four-winged appearance. It may have glided between trees or used its feathers for controlled movement through the air. Other feathered dinosaurs may have used their arms for display rather than flight. The fossil record shows that the path to birds was not a single straight ladder, but a branching bush of related experiments. Some feathered dinosaurs moved closer to flight, others remained grounded. Some had feathers for display, some had wing-like limbs but did not become true birds. Evolution explored many possibilities, and only one surviving branch eventually led to modern birds. The question of how flight began has inspired several major ideas. One idea suggests that bird ancestors were tree-climbing animals that first glided downward from branches, gradually improving control and lift. Another suggests that they were ground-running animals that used feathered arms to help leap, balance, turn, or pursue prey. A related idea, based partly on modern young birds, proposes that feathered limbs may have helped animals run up inclined surfaces by flapping, giving them better traction and control. These ideas are not necessarily mutually exclusive. Different feathered dinosaurs may have used their limbs in different ways, and the transition to flight may have involved climbing, leaping, gliding, running, display, and balance at different stages. What matters is that flight did not arrive as a miracle.
It emerged from bodies already suited for agility, feathers already useful for other functions, and forelimbs already capable of movement beyond ordinary walking. As birds evolved, their skeletons changed. The body became lighter, though not weak. Many bones became hollow or air-filled, connected to an efficient respiratory system. The tail shortened from a long, bony structure into a compact support for tail feathers. The hand bones became modified and fused. The breastbone became larger in later flying birds, providing attachment for powerful flight muscles. The shoulder joint changed to allow a strong wing stroke. Teeth eventually disappeared in modern bird lineages, replaced by beaks, though many early birds still had teeth. The skull became lighter and more mobile. These changes did not happen all at once, and early birds were diverse. Some lived in forests, some near water. Some may have eaten insects, fish, seeds, small animals, or mixed diets. During the Cretaceous, birds diversified alongside pterosaurs, which had already ruled the skies for many millions of years. Birds did not instantly replace pterosaurs. They shared the world with them, often occupying different ecological roles. Many Cretaceous birds still looked unusual by modern standards, with teeth, clawed wings, and body proportions unlike familiar living species. Yet they were becoming more bird-like over time, and some lineages developed strong flight abilities. Birds also inherited more than anatomy from their dinosaur ancestors. They inherited behaviors. Nesting, egg-laying, brooding, display, and perhaps forms of parental care all have deep roots in theropod dinosaurs. Fossils of oviraptorosaurs sitting over nests show postures strikingly similar to brooding birds. The arrangement of eggs in some dinosaur nests, the structure of eggshells, and the use of feathers to cover eggs all suggest continuity between non-bird dinosaurs and birds. Even the way birds move can feel like a living echo of theropod ancestry. The quick head movements, alert eyes, clawed feet, and balanced bodies of many birds reveal their dinosaur heritage in everyday life. A chicken scratching the ground, an ostrich running across open land, a crow studying its surroundings, or a hawk gripping prey with its talons, all carry fragments of this ancient story. The end Cretaceous extinction, about 66 million years ago, destroyed all non-bird dinosaurs, along with pterosaurs, mosasaurs, plesiosaurs, ammonites, and many other groups. But some birds survived. Why they survived when so many close relatives vanished remains a major question. But size, diet, habitat, seed-eating ability, flight, and ecological flexibility may all have mattered. The surviving birds were not the grand diversity of all Cretaceous bird life, but a limited group that passed through the catastrophe and later diversified into the thousands of species alive today. After the extinction, with pterosaurs gone and many ecological spaces empty, birds expanded dramatically. They became swimmers, divers, runners, singers, predators, scavengers, seed-eaters, nectar feeders, forest dwellers, ocean wanderers, and city survivors. From tiny hummingbirds to giant ostriches, from penguins to eagles, from parrots to crows, modern birds represent the continuing dinosaur story. This changes the meaning of extinction. The age of the great non-bird dinosaurs ended, but Dinosauria itself did not vanish. It changed form. The origin of birds shows that evolution is not always a story of disappearance. Sometimes it is a story of transformation. The same deep lineage that produced sickle-clawed hunters, feathered gliders, and small Jurassic flyers eventually produced the birds that fill modern skies with movement and sound. When we look at birds today, we are seeing the only surviving dinosaurs, not as fossils, but as living animals, breathing, nesting, calling, migrating, displaying, and adapting. Their feathers are ancient inventions. Their eggs continue an old reproductive tradition. Their bones preserve the memory of theropod bodies. Their behavior carries echoes of Mesozoic life. The origin of birds is therefore not a side chapter in the dinosaur story. It is one of its most important conclusions. It tells us that the dinosaur age never fully ended. Part of it took wing and continued into the present. Chapter 18. The Last Days of the Dinosaurs. The last days of the dinosaurs did not look like the end of the world at first. If a person could have stood in western North America, Asia, South America, Europe, or Africa near the very end of the Cretaceous period, about 66 million years ago, they would not have seen a dying planet filled only with weak and fading animals. They would have seen a world still alive with movement, color, danger, and abundance. Dinosaurs had ruled land ecosystems for more than 160 million years, and many groups were still successful. Herds of hadrosaurs moved across floodplains. Triceratops and other horned dinosaurs browsed among low plants and faced rivals with massive skulls. Ankylosaurs carried their armor through forests and open habitats. Tyrannosaurs stood at the top of food chains in some northern regions, while abelosaurids and other predators ruled elsewhere. Small feathered theropods darted through vegetation, stealing eggs, hunting insects, chasing lizards, or displaying to one another with feathers and calls. Birds flew through trees and along coastlines. Pterosaurs crossed the skies. In the seas, mosasaurs and plesiosaurs hunted fish, ammonites, turtles, and other marine life. Flowering plants were spreading through many landscapes. Insects were diversifying alongside them, and mammals, though mostly small, lived in burrows, trees, and shadows. The final Cretaceous world was not empty. It was complex, mature, and full of life. That is what makes its ending so powerful. The non-bird dinosaurs did not simply fade away because they were obsolete. They were still part of functioning ecosystems when catastrophe arrived. The geography of the late Cretaceous was already much closer to the modern world than the ancient supercontinent Pangaea had been, but it was still unfamiliar. The continents were separated by widening oceans, and sea levels were high. In North America, a great inland sea had divided the continent for much of the Cretaceous, though by the very end it was shrinking and retreating. Coastal plains, river systems, swamps, forests, and seasonal floodplains provided rich habitats for dinosaurs. In what is now the western United States and Canada, the famous Hell Creek ecosystem preserved a snapshot of the very end of the age. There lived Tyrannosaurus rex, Triceratops, Edmontosaurus, Ankylosaurus, Pachycephalosaurus, smaller theropods, turtles, crocodile relatives, fish, amphibians, mammals, birds, insects, and many kinds of plants. This was not a simple landscape with one predator and one prey animal. It was a complete, living community. Rivers shifted across broad plains. Floods buried carcasses in sediment. Forests included conifers, ferns, palms, and flowering plants. Seasonal changes brought wet and dry periods. Young dinosaurs hatched from eggs, grew rapidly, and faced predators long before they reached adult size. Old animals carried scars and healed injuries. The world had rhythms, and those rhythms continued right up to the edge of disaster. In other parts of the world, the last dinosaurs looked different. In Asia, tyrannosaurs such as Tarbosaurus hunted large herbivores, while oviraptorosaurs, ankylosaurs, hadrosaurs, and ceratopsians occupied varied roles. In South America, abelosaurids were among the dominant predators, and titanosaurs, the last great sauropods, still carried the legacy of long-necked giants. In Europe, many dinosaurs lived on islands created by high sea levels, and some evolved smaller body sizes in response to limited resources, a phenomenon known as island dwarfism. In India, Tyrannosaurs roamed lands that were moving northward toward Asia, while immense volcanic eruptions were beginning to transform the environment. Across the planet, dinosaur life was regional and diverse. There was no single final dinosaur world. There were many final worlds, each shaped by its own geography, climate, plants, and evolutionary history. Some dinosaur groups may have been declining in certain regions before the end, and scientists continue to debate how healthy global dinosaur diversity was in the last few million years of the Cretaceous. Fossil records are incomplete, and some places preserve the final chapter better than others. But the broad picture is clear enough. Many dinosaurs were still present, still reproducing, still evolving, and still ecologically important. Their extinction was not the quiet disappearance of a failed lineage. It was the violent interruption of a long, successful one. The late Cretaceous was also a time of environmental pressure even before the asteroid impact. Sea levels changed, climates shifted, and volcanic activity in India, known as the Deccan Traps eruptions, released enormous amounts of lava and gases over time. These eruptions may have affected climate, ocean chemistry, and ecosystems, possibly stressing some species before the final disaster. The world was not perfectly stable. Earth never is. But life had endured climate swings, volcanic events, sea level changes, and ecological turnover many times before. Dinosaurs had survived previous crises, including the Triassic-Jurassic extinction that helped launch their dominance. They were resilient animals, but resilience has limits when catastrophe becomes global, sudden, and severe. Before that final moment, the last dinosaurs lived ordinary lives in extraordinary bodies. A Triceratops did not know it belonged to the last generation of a mighty lineage. A Tyrannosaurus did not know it would become the symbol of a vanished world. A hadrosaur, nesting beside a river, did not know the sky itself would soon change. Their lives were immediate, ruled by food, danger, reproduction, weather, territory, and instinct. This is important because extinction often looks inevitable only when seen backward. From the viewpoint of the animals themselves, the future was still open. The sun rose over Cretaceous forests, rivers carried sediment toward the sea, insects moved among flowers, a small mammal searched at night, a pterosaur lifted from a coastal cliff, a young dinosaur followed the movement of a herd. Life continued with no awareness that it stood at the edge of one of the greatest turning points in Earth's history. The last days of the dinosaurs were therefore both normal and tragic. Normal because ecosystems still functioned, animals still behaved according to ancient patterns, and the planet was still alive with familiar cycles. Tragic because those cycles were about to be broken by an event from beyond the everyday world. An asteroid, roughly 10 kilometers wide, traveling at cosmic speed on a collision course with Earth. It would strike in what is now the Yucatan Peninsula of Mexico, forming the Chicxulub crater and unleashing energy beyond anything in recorded human experience. But before the impact, there was a final Cretaceous morning, a final season, a final generation. Somewhere, a dinosaur hatched from an egg. Somewhere, a predator followed the scent of prey. Somewhere, a herd crossed a muddy plain and left footprints that might have lasted long enough to fossilize. Somewhere, birds called in the branches, unaware that their descendants would become the only dinosaurs to survive. The last days of the dinosaurs were not a slow curtain closing on an exhausted age. They were a living world interrupted. That is why this chapter matters. It reminds us that extinction is not always preceded by weakness, and survival is not always granted to the strongest or most famous. The non-bird dinosaurs had filled the earth with giants, hunters, armored defenders, horned herbivores, feathered forms, nesting colonies, migrations, displays, and ancient voices. They had shaped the land for millions upon millions of years, and then, in a geological instant, their world approached its final test. Chapter 19. The Great Extinction. The Great Extinction at the end of the Cretaceous was one of the most dramatic turning points in the history of life. For more than 160 million years, dinosaurs had dominated the land. They had survived changing climates, shifting continents, volcanic eruptions, rising and falling seas, competition, and earlier extinction events. They had become giants, hunters, armored defenders, horned herbivores, feathered animals, nesting parents, herd travelers, and eventually, birds. But about 66 million years ago, the world changed with extraordinary violence. An asteroid, roughly 10 kilometers wide, struck Earth in the region that is now the Yucatan Peninsula of Mexico. The impact created the Chicxulub crater, a vast scar buried beneath later rocks and sediments. The energy released was almost unimaginable. It was not like a normal volcanic eruption, earthquake, or storm. It was a planetary-scale disaster, powerful enough to alter the atmosphere, oceans, climate, forests, and food webs across the entire globe. In the immediate region of impact, destruction would have been total. Rock was vaporized, shock waves blasted outward, earthquakes shook the crust. A massive plume of superheated material rose into the sky. Tsunamis may have surged through nearby seas, tearing across coastlines and carrying debris far inland. Forests were flattened or burned. Animals near the impact zone had almost no chance of survival. But the true horror of the extinction was not limited to the crater. The asteroid did not merely kill what stood nearby. It changed the conditions of life everywhere. Dust, soot, sulfur compounds, and pulverized rock were thrown high into the atmosphere. Some material fell back through the air as burning debris, possibly heating the atmosphere and igniting wildfires across wide regions. The sky darkened. Sunlight struggled to reach the surface. Photosynthesis, the foundation of most food chains, was disrupted. Plants died or stopped growing normally. In the oceans, plankton communities collapsed. On land, forests were damaged or destroyed in many places. The world entered a period sometimes described as an impact winter, when darkness, cooling, acid rain, and ecological shock placed unbearable pressure on living things. For large animals that needed great amounts of food, the crisis was especially severe. A giant herbivorous dinosaur could not simply wait for years while plant communities recovered. A large carnivore could not survive long once its prey disappeared. Food webs that had taken millions of years to develop began breaking apart in a geological instant. The extinction did not kill every animal in the same way or at the same moment. Some died immediately from fire, shock waves, tsunamis, or falling debris. Others survived the first day, the first week, perhaps even the first months, only to face hunger, cold, darkness, poisoned environments, and collapsing ecosystems. Eggs failed. Young animals starved. Herds lost food sources. Predators followed weakening prey until there was not enough left to sustain them. Rivers, lakes, burrows, seeds, and aquatic food chains may have provided refuge for some creatures, but not for all. This difference in survival is one of the most important mysteries of the extinction. Non-bird dinosaurs vanished, but some birds survived. Pterosaurs disappeared, but certain bird lineages endured. Mosasaurs and plesiosaurs vanished from the seas, but crocodilians survived. Ammonites disappeared, but nautiluses survived. Many mammals survived, along with turtles, frogs, lizards, snakes, insects, fish, and other groups. Survival was not simply a matter of strength. In fact, many of the most powerful animals died. The survivors often had traits that helped them pass through a broken world. Small body size, flexible diets, burrowing habits, freshwater habitats, ability to eat seeds or detritus, slower metabolisms, protected eggs, or ecological positions less dependent on fresh green plants. Small mammals could hide, eat insects, seeds, roots, or scraps, and reproduce relatively quickly. Crocodilians could survive long periods without food and live in aquatic environments buffered from some immediate land-based collapse. Turtles and amphibians may have benefited from freshwater systems that retained food sources longer than open terrestrial ecosystems. Some birds, especially ground-dwelling or seed-eating forms, may have survived because seeds could remain edible after forests collapsed. Many other birds, including toothed Cretaceous lineages, died out. The survivors were not all birds. They were a narrow remnant of a much larger avian world. The Great Extinction was therefore both selective and brutal. It did not erase life randomly, but neither did it reward the creatures humans might call superior. It favored those whose lifestyles happened to fit the disaster. The non-bird dinosaurs were caught in a terrible trap. Many were large, many depended directly or indirectly on abundant vegetation. Many laid eggs in exposed nests. Many lived in food webs built around active plant growth. Even smaller non-bird dinosaurs, including feathered theropods, disappeared, perhaps because their diets, habitats, or reproductive strategies were not flexible enough for the post-impact world. The asteroid was probably the final blow, but Earth was already under pressure. The Deccan Traps eruptions in India had released vast amounts of volcanic gases over a long period, possibly affecting climate and ecosystems before and after the impact. Scientists continue to debate the exact relationship between volcanism and asteroid impact, but the evidence strongly shows that the Chicxulub impact was the decisive event at the boundary. In rocks around the world, the Cretaceous-Paleogene boundary is marked by a thin layer enriched in iridium, an element rare in Earth's crust but more common in asteroids. That layer is like a timestamp of catastrophe, a chemical whisper of the day the sky changed. Below it lie the fossils of the Cretaceous World. Above it, the non-bird dinosaurs are gone. The aftermath was not immediate peace. The early Paleogene world was one of recovery. Ferns may have spread quickly in some devastated landscapes, creating what scientists call a fern spike, a sign of ecological disturbance after forests were damaged. Food chains rebuilt slowly. Mammals, once mostly small members of ecosystems dominated by dinosaurs, began to diversify into newly empty roles. Birds expanded into the skies left vacant by pterosaurs and extinct bird lineages. Crocodilians, turtles, fish, insects, and surviving plants continued into the new era. Life did not end, but it was redirected. The asteroid did not destroy evolution, it changed its path. Without the extinction, mammals might never have become the dominant large land animals of the Cenozoic. Primates might never have evolved in the same way. Humans might never have appeared. In this sense, the death of the non-bird dinosaurs is connected, distantly but profoundly, to our own existence. Yet it should not be seen only as a necessary opening for mammals. It was also the end of an immense and successful world. Tyrannosaurus, Triceratops, Edmontosaurus, Ankylosaurus, Titanosaurs, Abelisaurids, Hadrosaurs, Ceratopsians, and countless smaller dinosaurs vanished forever. Their calls stopped. Their nests emptied. Their herds disappeared. Their footprints no longer crossed fresh mud. Only birds carried the dinosaur lineage forward. The Great Extinction reminds us that life on Earth is powerful but vulnerable. A group can dominate for millions of years and still fall in a moment of planetary upheaval. Size, strength, armor, teeth, horns, speed, and long success are not guarantees against catastrophe. The end Cretaceous extinction was not just the end of the dinosaur age. It was a demonstration of how deeply life depends on stable sunlight, climate, plants, oceans, and atmosphere. When those foundations are shaken, even the greatest animals can vanish. And yet, from the ashes, life continued. The world after the impact was poorer at first, quieter, darker, and emptier. But it was not dead. Seeds sprouted, ferns spread, mammals emerged from hiding, birds survived and began again. The dinosaur age ended in fire, darkness, hunger, and silence. But one feathered branch endured, carrying the memory of that lost world into every forest, field, coast, and city where birds still live today. Chapter 20. Dinosaurs. After dinosaurs. The story of dinosaurs did not truly end when the asteroid struck Earth 66 million years ago. The great non-bird dinosaurs vanished, the pterosaurs disappeared from the skies, the marine reptiles were erased from the oceans, and the world entered a new era. But one branch of the dinosaur family survived. Birds carried the dinosaur legacy through the catastrophe and into the modern world. Every sparrow, eagle, ostrich, penguin, crow, swan, and hummingbird is part of that surviving lineage. This means that dinosaurs are not only creatures of museums and fossil beds, they are also living animals that still fly, sing, nest, migrate, hunt, display, and adapt around us. The phrase, after dinosaurs, is therefore partly misleading, because after the extinction came a world without Triceratops, Tyrannosaurus, Ankylosaurus, or Edmontosaurus, but not a world without dinosaurs completely. The age of the giant, non-bird dinosaurs ended, while the age of bird dinosaurs continued. In the first years and centuries after the impact, the planet must have been a difficult and damaged place. Forests had burned or collapsed in many regions. Food chains were broken. Large herbivores were gone. Large predators were gone. The old Mesozoic order had disappeared. But life is persistent, and recovery began unevenly across the planet. Ferns, often among the first plants to colonize disturbed ground, spread in some devastated landscapes. Surviving seeds sprouted. Insects, fungi, freshwater animals, small reptiles, turtles, crocodilian relatives, amphibians, fish, mammals, and birds endured in scattered refuges. The early Paleogene world was not an instant paradise for mammals or birds. It was a recovery world shaped by absence. The enormous ecological roles once filled by dinosaurs were suddenly empty. There were no sauropod herds moving through forests, no hadrosaur nesting colonies along river plains, no tyrannosaurs patrolling floodplains, no horned dinosaurs testing rivals with their skulls. Into this emptiness, surviving groups began to expand. Mammals diversified rapidly compared with their earlier Mesozoic history. Birds also spread into new forms, taking advantage of skies no longer shared with pterosaurs and ecosystems newly opened by extinction. Over millions of years, birds became swimmers, divers, runners, seed-eaters, predators, scavengers, forest dwellers, shorebirds, songbirds, and ocean wanderers. Some became giants themselves, though on a very different scale from the dinosaurs before them. Flightless birds, such as the terror birds of South America, became powerful land predators in the Cenozoic. Giant moas later lived in New Zealand, towering over humans before they were hunted to extinction. Elephant birds lived on Madagascar, producing some of the largest eggs known from any animal. Ostriches, emus, cassowaries, rheas, and kiwis are modern reminders that bird dinosaurs did not only conquer the air, some returned fully to the ground. Meanwhile, the remains of the non-bird dinosaurs slept inside rock. For tens of millions of years, their bones lay buried beneath sediments, turned slowly into fossils by mineral-rich water, pressure, chemistry, and time. Rivers exposed some bones and destroyed others. Mountains rose and revealed ancient layers. Deserts, cliffs, badlands, and quarries became windows into vanished worlds. Humans arrived very late in this story, and long before science understood fossils properly, people sometimes found great bones and tried to explain them through myth. Ancient discoveries may have inspired legends of giants, dragons, griffins, and monsters, though such connections are often difficult to prove with certainty. What is clear is that fossil bones challenged imagination long before they became part of modern paleontology. In the 19th century, dinosaurs began to return to human awareness as scientific creatures. Early fossil discoveries in Britain and elsewhere led researchers to recognize that these bones belonged to extinct reptiles unlike anything alive today. The word dinosaur was introduced in 1842 by Richard Owen, meaning terrible lizard, though the animals were not actually lizards. At first, dinosaurs were often imagined as huge, heavy, sluggish reptiles. Early reconstructions were incomplete and sometimes inaccurate, but they captured public attention. Dinosaur skeletons entered museums, and museums turned them into icons of deep time. To stand beneath a mounted dinosaur skeleton was to feel the scale of Earth's history in a direct, physical way. Later discoveries transformed the science again and again. In North America, the famous bone wars of the late 19th century produced many new dinosaur fossils, including sauropods, stegosaurs, and theropods, though the rivalry between paleontologists was often chaotic and destructive. In the 20th century, expeditions in Mongolia, Africa, South America, and China revealed eggs, nests, new species, feathered dinosaurs, and entire fossil ecosystems. Ideas changed. Dinosaurs were no longer seen as evolutionary failures. They became active animals, diverse, adaptable, and deeply connected to birds. The dinosaur renaissance of the late 20th century reshaped public and scientific understanding, emphasizing metabolism, behavior, speed, posture, and the bird connection. Then, feathered dinosaur fossils made the connection unmistakably vivid. Suddenly, the old image of dull, scaly monsters gave way to a richer vision. Animals with feathers, colors, display structures, parental care, social behavior, and complex lives. Dinosaurs also became part of popular culture in a way few extinct animals ever have. They appeared in books, films, toys, documentaries, cartoons, video games, school lessons, museum halls, and children's imaginations. Sometimes these portrayals were scientifically outdated, exaggerated, or completely fantastical, but they kept dinosaurs alive in culture. Tyrannosaurus rex became a symbol of prehistoric power. Triceratops became the noble horned defender. Velociraptor became famous, even though popular versions often looked very different from the real animal. Long-necked sauropods became symbols of impossible size. Dinosaurs gave people a way to feel wonder about nature, extinction, time, and the strange creativity of evolution. They are educational gateways. Many children first encountered geology, biology, evolution, climate change, extinction, and scientific discovery through dinosaurs. But the real dinosaurs are even more interesting than the monsters of imagination. They were animals shaped by ecosystems, not villains or heroes. Their fossils teach us about ancient climates, continental drift, evolution, growth, disease, reproduction, and catastrophe. A single bone can reveal age and growth rate. A tooth can reveal diet. A footprint can reveal movement. A nest can reveal reproduction. A feather impression can reveal appearance. A layer of rock can reveal the environment in which an animal lived and died. Modern paleontology uses tools that earlier scientists could hardly imagine: CT scanning, isotope analysis, biomechanical modeling, microscopic bone studies, computer simulations, and comparisons with living animals. These methods allow researchers to ask not only what dinosaurs looked like, but how they moved, how fast they grew, how they breathed, what they ate, how they sensed the world, and how they changed across evolution. Yet dinosaurs also teach humility. The fossil record is incomplete. Most animals never fossilized. Many species remain unknown. Soft tissues, colors, calls, mating rituals, and daily behaviors are often lost or only partly recoverable. Every reconstruction is a careful mixture of evidence and uncertainty. Science does not bring the past back perfectly. It approaches it, revises it, and improves it as new evidence appears. After dinosaurs, the world became the world of mammals, birds, flowering plants, grasslands, whales, bats, primates, and eventually humans. But the vanished dinosaurs remained part of that story. Their extinction opened ecological space for mammals. Their surviving bird descendants filled the skies. Their fossils shaped human understanding of deep time. Their disappearance became one of the clearest warnings that even dominant life forms can be vulnerable to planetary change. Today, when a bird lands on a windowsill or crosses the sky, it carries a living thread from the Mesozoic. When a museum skeleton stands under bright lights, it carries the mineral memory of a lost body. When scientists uncover a new fossil from desert stone, another sentence is added to a book that began more than 230 million years ago. Dinosaurs after dinosaurs are therefore both absence and presence, absent in their giant non-bird forms, present in birds, fossils, science, and imagination. Their age ended, but their story did not. It continues in every fossil discovered, every theory revised, every bird that takes flight, and every person who looks at the bones of a vanished giant and feels the enormous depth of Earth's history.